presentations as well as super exciting keynotes. Let us begin.
Artificial intelligence. We objectively assess the importance of this topic. However, there is still no consensus on whether all tasks can be solved using these technologies. Abuse or obligatory use. We will raise such issues of ethics, modern information society, and cybernetics. This is the story of our virtual conference on pattern recognition and information processing in 2021, which has already begun. Here, right now.
And now, after this awesome intro, I would like to introduce speakers of our first, let's say, opening session. So, General Director of United Institute of Informatics Problems, Professor Dr. Alexander Tuzikov, Chairman of the conference. Academician of the National Academy of Sciences of Belarus, Professor Sergei Blameiko, Conference Vice Chairman. And our distinguished guest, Academician of the National Academy of Sciences of Belarus, Professor Sergei Gaponenko, who is the head of Belarusian Republic Foundation for Basic Research. So, Chairman, please, you have a floor now.
Okay, thank you very much, Alexei. I'm very glad to host this conference, 15th International Conference on Pattern Recognition and Information Processing in our institute. So this conference has already 30 years history, and now we host this conference in our institute. Unfortunately, as Alexei told, it's difficult to organize the conference in offline sessions, and it's clear why. Because of pandemic constraints, it's difficult to move, to come to our country, our city, our institute to participate at this conference. But from the other side, we have some advantages of this online mode of the conference, because we were able to invite and we got exceptions from them, very bright researchers working in this area, and we are happy that we will have the opportunity to listen this brilliant presentation from our plenary speakers. Our conference was organized 30 years ago, and it was like the main event of our association of image analysis and recognition. And that time we organized it in English. However, we understood that it would be very difficult for us to have this conference in English, but it was necessary to integrate in this space of International Association of Pattern Recognition to be like in the united family of people working in this area. And now we are very glad that we have this conference here in Minsk, and I like very much to open this conference. And I would like to give the floor to Professor Sergei Blameiko, who is head of our National Belarusian Association of Image Analysis and Recognition. Please.
Thank you, Alexander. It's my great pleasure to be here in the 15th International Conference on Pattern Recognition and Information Processing. As my colleague said, 30 years ago, exactly in autumn 1991, we organized here in this institute the first conference. It's called Pattern Recognition and Image Analysis, and at that time it was all Union Soviet conference in this area. It was the first one even. And then we started to organize like Belarusian society, IPR society, this conference. Approximately 25 years already this conference is going under auspices of International Association for Pattern Recognition, and we are very grateful for UIIP for permanent support of this conference. This conference allows us to organize, to invite, to have scientists from, first of all, of course, Central Eastern European, from other European countries. And I would say that especially this today conference, we had papers from more than 15-20 countries. And this is really very good. And you can see program, and it's quite a good program. And of course, and also specifics of this year conference. First time we organize conference online, and it's really not easy, but it's a new experience. Alexander Tuzikov said that it allowed us to invite distinguished speakers from all over the world, and there is no necessity to personally come in Minsk, but we will have nice, brilliant presentations from very famous scientists. So we are happy that already 30 years, every practically 2 years, we have such a conference. And I would like to wish success for our 15th International Conference, Pattern Recognition, Information Processing. And of course, I wish to good health for all participants of our conference and success to the conference. Thank you. And I will pass microphone to our distinguished guest, academician Sergei Gaponenko.
Thank you so much, Sergei. Dear friends, dear colleagues, it is my honor and pleasure to join for some period your excellent community. You really facing challenges, as mentioned in the subtitle of your conference, and you see, I do not believe to IT community myself. I'm IT user, I would say. I'm physicist. When I was a PhD student, something like 40 years ago, I used the first computer in my life. It was a big collective use facility in our Institute of Mathematics. And there was a big hall, a lot of metal boxes, and you see service team, something like 10 people continuously served to enable this facility to work. I feel that at that time, nobody could really foresee the tremendous progress in this field, which your community did actually for us. And nobody foresee at that time that we will have computers in every pocket, and actually computer will become, and it is, an image-making gadget of junior schoolboy nowadays. And this is actually a challenge which you did, which you implemented and performed for everybody, I represent here our Basic Research Foundation, which supports many projects, research projects. We consider that basic research is the very first, and I would say very cheap, stage of innovation chain. And we are happy to have many applications from senior scientists and also from young researchers in the field of IT. And I would like to add that we have very nice preferences for IT activity at all in our country. We have unbelievable, extraordinary preferences, economical preferences and financial preferences for IT business and IT services. I wish success to your nice event, and again, thank you for inviting me, and I'm really happy to be here today. Thank you.
Okay, thank you very much, distinguished guests. Now, ladies and gentlemen, I would like to tell some tips to draw attention to getting the best of the online event. We have speakers, presenters, let's say, and listeners. I hope that everybody who would like to present their papers already formalized themselves and timing and has connected during the session, get together. And if you will have your presentation other sessions, you will have time to connect during breaks. We got this awesome studio. So it is a main focus of the conference. Our team is moderating you and switching the focus to the current speaker. When you have a floor, please share your screen and so present your material in any proper manner. You have around 10 and 12 minutes to presentation and 5-3 minutes for questions from the audience, from participants at Zoom, as well as from the audience at the stream. Yes, we have streamed to the YouTube stream, and now I'm addressing to that audience. Please do not hesitate asking questions in the chat, YouTube chat, which is on the right corner of your screen, and join our Telegram chat. The link is in the YouTube description below. Go also to the website to navigate through the website to find the program in the appropriate session and learn about speakers and find abstract in the program session. At least please subscribe to our YouTube channel and follow. We are also in the social nets, so post whatever you want about the conference, about this event with hashtags, hashtag PRIP, hashtag PRIP'2021, hashtag PRIP'2021 online. So now I'm closing this session. Thank you, our distinguished guests, and I would like to open the first plenary session, which will be chaired by our General Director, Professor Tuzikov. So, Professor, again, you have a floor now.
Okay, thank you very much, Alexei. I'm very glad to start the first plenary session, and I would like to introduce our distinguished speaker, Jos Roerdink, professor, who is working in the university, in Groningen University in the Netherlands. His talk, generalization of mathematical morphology and their application to the processing of scalar, vector, tensor images. Jos, it's very nice to see you. I'm very glad. I would like to make a short introduction about your activity. I would like to say that Jos received his PhD in theoretical physics in 1983 from the University of Utrecht in the Netherlands. Then he had a postdoctoral position at the University of California in San Diego, and after he joined the Center of Mathematics and Computer Science in Amsterdam. And since 1992, he was appointed associate professor at the University of Groningen, and since 2003, he has been full professor of scientific visualization and computer graphics. And also, I would like to say that last 3 years, Jos was director of Johan Bernoulli Institute for Mathematics and Computer Science in the University of Groningen, where he currently holds a chair in scientific visualization and computer graphics. I would like to say that Jos is very well known in his contribution in various areas related to image processing and pattern recognition, especially in mathematical morphology, biomedical visualization, neuroimaging, and bioinformatics. I would like to say that I'm also happy that I spent in 1996 2 months in Jos group working in the area of mathematical morphology. Now I would like to give the floor to Professor Jos Roerdink to present this talk on mathematical morphology. Please, Jos.
Thank you very much, Alexander. Let me first say that I have also very fond memories on our collaborations in the 90s and the contacts we kept over the years. So it's with pleasure that I present this talk. So let me share my screen. And let's see whether this works. have to give permission. So can you see my screen now?
Not yet.
Not yet.
Not yet. We will check. Yes. Please wait a bit.
Share. How about now?
Now, yes. Now we see your screen.
Okay, very good. So I'm going to talk about mathematical morphology, which is one of the topics in image processing I've been working on for many years, actually starting in my period at the Center for Mathematics and Computer Science in Amsterdam. As Alexander mentioned, I've also later started to work on other topics like visualization and graphics, but today I will focus on mathematical morphology. And actually, the goal of my talk is to present a kind of a summary of almost 30 years work on this topic, starting from simple, straightforward morphology, and then gradually extending it to very different types of images. So let's see. I would like to start with just a very quick summary of mathematical morphology for those who might not be so familiar. So first of all, I should say that what morphology is doing is working on shapes in the images. So in contrast, say, to linear image processing, which typically works with convolutions, Fourier transforms, etc., mathematical morphology works with the concepts of shapes. And it formalizes this by using the mathematical theory of sets, that is for binary images, and later also functions for grayscale images. But let's start with, say, binary images. What is very nice about mathematical morphology is that it allows a very nice geometrical interpretation. So since it works with shapes in the image, it allows the researcher and also the general, say, interested layman to understand intuitively what these operations are doing. So on the one hand, we have this geometric intuition, which also allows us to invent new algorithms. On the other hand, we have a formulation of these intuitions in terms of very precise algebraic notions. And those are typically used to implement the algorithms. It can be extended to gray value images, and I will present this in a minute. So what are the basic definitions for binary images in morphology? So first you start with an image space, typically denoted by E, could be n-dimensional Euclidean space or discrete space, Zn. And as we work with sets, the mathematical say notion which is involved here is the power set. So you take your image space E, and then you consider all the subsets of that space E, and that collection of subsets is the power set P of E. We have an ordering on this space, set inclusion. So this is important because later we are going to look at other orderings. And we have to define, when we have a set X, what we mean by the translate of X, which is denoted by X sub A. So if A is a vector, then we can translate any set over that vector and call it X sub A. And then we can define the basic operations in binary morphology, which are dilation and erosion, which essentially are Minkowski addition and subtraction. So you see the formula X plus A, plus with a circle around it, is the union of all translated sets XA, where A runs over the set capital A, which we call the structuring element. And for the erosion, you see the formula where you have intersections instead of unions, and there is the minus A. For convenience, I'm not going to explain it in detail, but that has some advantages to have minus A here instead of plus A. As soon as you have these basic operations, you can define composite operations. And the first important ones are the opening and the closing. So the opening, X circle A, is an erosion, x minus a, followed by a dilation, plus a. And for the closing, it's the other way around. And these operations are different. So dilation and erosion, in general, do not commute. Therefore, you can define these two operations, opening and closing. So here's a geometrical interpretation for dilation and erosion. Suppose we have a very simple set X, which is a rectangle, and a structuring element A, which is a circle. Then geometrically, what the dilation is doing is taking the structuring element and putting it on all the points of X, and then taking the union of all those translates. And so the new set is defined by this curved border, which you see here. For the erosion, what the operation is doing is it takes the structuring element and looks at all the locations where the structuring element fits completely inside the set X. So you can see here, what you get is a new rectangle. The boundary case is where you put the circle here, where it just fits inside the original rectangle X. For the opening, there's also a very nice geometrical interpretation. So X circle A, the opening of X by A, is the union of all the translate which fits inside. So in contrast to the erosion, you do not collect the points A, but the whole translated set. So if you look at this example, a rectangle and a circular structuring element, you're going to put the structuring element everywhere inside X, where it fits, and then you take the union. So you will get a new set, which is this set where the corners are rounded because the structuring element can no further than this point. What is very important, and also for my talk, essential, is to look at the concept of translation invariance. So the idea of translation invariance is the following. If you take a set X and a structuring element, you can translate, say, the set so that you get a new set, X sub H, and then do a dilation, you get a result. Or what you can do is first dilate the result by the structuring element and then translate the result. And you get the same. This we call translation invariance. In this case, for the dilation, you have the same for erosion, opening, closing. So in formula, what translation invariance says is if you take a dilation and you translate it over a vector, what you can do is also first translate the set over that vector and then do the say dilation, and the result will be identical. So this we call translation invariance. It's just translating sets over the image plane. Here's the extension to grayscale images. So now we have not a set, but a function, a grayscale function. And we have, say, another function B, which we call the structuring function. We use the same notation. So the dilation F plus B is, instead of having unions like in sets, we now have the maximum. So you look at the function at a certain point, xy, and then you're going to look at all translation vectors inside the structuring function, and you collect the maximum of all those, say, function values which you get. In this case, the structuring function is flat, meaning it's like indicated here. It has a constant value. It can be generalized to structuring functions which are non-flat, but this is the simplest case. For erosion, you get a similar formula. Instead of maximum, you now have minimum. So these filters are sometimes also called max-min filters. Again, as soon as you have dilation and erosion, you can follow up by defining the opening and the closing. Again, the iterates first erode, then dilate for the opening, or first dilate, then erode for the closing. So if you look at this one-dimensional example, essentially what the erosion does is it takes this flat structuring element, moves it vertically as long as it fits under the graph of the function. And then the result will be the opening. So it will be kept here, say, at the local maxima. And for the closing is the other way around. It will fill, say, valleys. On the right, you see an example where you have an input image on the top left corner. And then you have dilation, erosion, and opening. So this is the summary of standard morphology. Now to generalize this, you can go many different ways. So essentially morphology has two elements. It has the idea of sets or functions, and it has the idea of some operation under which the operators are invariant. So for the binary morphology, it was translation invariance. You can replace it by other invariants. So you look at different ways in which you can, say, move structuring elements around, not just by translation, but maybe also by rotation, scaling, or even more general, say, operators. And what you get is what is called group morphology. So I will give some example in a minute. You can also look at the spatial element and then look at structuring elements which are not fixed any longer, but which may depend on position, or maybe even depend on the input image. And then you get adaptive morphology. So I distinguish two cases where the structuring elements depend on the location, or where they depend on the input itself. And then we talk about input adaptive structuring element. It can also be extended to arbitrary complete lattices. So for the binary case, we had the lattice of P of E, this collection of subsets. You can have other complete lattices, but I will not focus on this in this talk. And you can extend it to other type of functions, not scalar functions, like in just grayscale images, but maybe vector function or even tensor data. So we will see how this can be done. So let's start with group morphology. I'm not going to focus on the mathematics, which is quite involved, but just show you some examples so that you get some intuition about what is happening. So if you look at the top left image, this is the case of Euclidean morphology. So you have, say, a black set, which may be the structuring element, and we can translate it to different, say, locations in the image plane. So essentially, all those black squares are copies of the structuring element. So apart from, say, the translation, they're identical. Now, if you look at the top right image, you get circular morphology. So instead of translation in horizontal and vertical directions, you get two other operations. You can rotate the structuring element, and you can scale it with respect to the origin. So again, if you say if this would be the basic structuring element, all the other black regions are essentially copies of the structuring element, and now not by translation, but by the, say, polar group of rotations and scaling. So if you have this intuition of moving the structuring element around, when you have this group, this is what it means to move the structuring element around. There's another example, perspective morphology, where you have the group of perspective transformations. And again, the blacks, say, regions in the image plane are just copies of the structuring element under the perspective group. What is important to realize is that in this case, the structuring elements do depend on position, if you look at, say, this representation, but they are independent of the input image. This is important to keep in mind. So if you want more details on this, you can, for example, look at my paper on group morphology, where I summarized, say, all the different groups which may be used in morphology. Also, the three examples which you see here are kind of special in the sense that the group involved is abelian. That means it is a commutative group. And if you look at other groups, they may become non-commutative, and then things become really more complicated. So let's look at this case. So what other groups can you imagine? Well, for example, similarity group, which means translation, rotation, and scaling, or the group of infinite transformation, or you can try to work on a sphere, you get spherical transformations, or even projective groups. And in all these cases, the group is non-abelian, which mathematically makes things much more complicated. And again, I refer to my group morphology paper for all the details, because there would not be enough time to discuss it today. One particular result which I found is that if you look at openings, as we have seen, say, in binary morphology, the opening by a structuring element, same for closings, there is a property in say, the Euclidean case that they can be decomposed in products of dilations and erosions, which are themselves group invariant. But for the general case, where the group is non-abelian, this is no longer true. And there are other properties which also no longer hold. Just an example, in this case, working on a sphere with the group of, say, spherical rotations. This is an example where on the left you see a picture of the planet Mars. And you do a grayscale opening, a spherical grayscale opening, using the theory of group morphology, and the result will be like you see in B. So the result of the opening is that small details are removed, values are filled. If you would be naive and consider image A just as say, a binary image or a grayscale image, a grayscale image on the plane, and just use Euclidean grayscale opening, then you get the result in C, which obviously is very different. And so you have to adapt the group to, say, the geometry of your problem. And so this is the result you can achieve. So I will stop here talking about group morphology and now go to adaptive morphology. So for adaptive morphology, there are two cases, and the first one is location adaptive structuring elements. So you can imagine that you have a space where there is a function n, which associates to each point of the space E a set. And this set may therefore be different for different points. Nevertheless, you can define the operation like you did for the standard Euclidean case, where the structuring element is fixed, of computing all the union of all the over all the points in the set X of the neighborhoods, say n, and we call neighborhoods, at that point X. So even although those neighborhoods depend on X, if you take the union of all those sets, you get a dilation. And why we call this a dilation? Well, the defining property is that it's invariant under union. So delta of X union Y should be equal to delta X union delta Y. And if you define the operation in this way, this property holds. So it is a proper dilation. Now, another interesting consequence of the theory, which actually was developed by many other people like Henk Heijmans from CWI in Amsterdam and Christian Rons, and of course originally by Jean Serrat and his co-workers. There is a notion of adjunction, meaning that as soon as you have a dilation, there is automatically an erosion associated to it. Below you see the definition of adjunction. I'm just going to display the formula. So once you have this dilation, you can define the erosion of the set X, which is the collection of all the points such that the neighborhood at Y is included in X. And actually what you observe in the literature is that very often people define delta and epsilon, so dilation and erosion, independently. And sometimes they no longer form an adjunction, but actually this is not necessary. So again, as soon as you have a dilation on a complete lattice, there is automatically an erosion associated with it, and vice versa. So if you look at grayscale functions, you can do the same, and the formulas are almost the same, except that instead of union, you now have supremum, or maximum, say. And instead of intersection, you have infimum, or minimum. And again, for example, for the dilation of a grayscale function at X, it's simply the maximum of all function values where Y ranges over the neighborhood, actually in this case, the reflected neighborhood. And the erosion is the infimum of the function values over the neighborhood. And in this way, they form a proper adjunction. As soon as you have an adjunction, you can define opening and closing. You know this automatically. And you know also that those products, delta epsilon and epsilon delta, will have certain properties. For example, an opening is idempotent. If you repeat it, you get the same result. It is increasing. And you have a number of properties and the third one is anti-extensivity. Those three properties will automatically hold. Now there's another case which people looked at in the literature, which is where the structuring element becomes a function of the input image. And this is really tricky because it's easy to write down a formula like this. So instead of a neighborhood which depends on the location, it also depends now on the input function. And same for erosion. So the neighborhood function, the reflected neighborhood function. So it seems a small change, but actually this is no longer, this pair delta and epsilon defined in this way is no longer a junction. And so if you form, say, iterates like epsilon followed by delta or delta followed by epsilon, the result is not an opening and a closing. And it took some effort over the years of finding out how this should be done. To do it properly. And actually what you can do is the following. First, you take an image F0, which we call a pilot image. And this first, say, input image is used to define the neighborhood functions. Once you have these neighborhood functions, you fix them, and then you can define dilations and erosions in this way. So now dilation depends on two inputs, the function, the image itself, say, and the pilot image. If you do things in this way, then indeed you have a proper dilation and erosion, and you can formulate iterates so that you have opening and closing. So again, this is a very short summary. If you're interested in the footnotes, there's a reference to a paper where I worked this out. Again, an example of such location or function dependent neighborhoods, which are the morphological amoebas, as presented by Leralu and co-workers in 2007. So the idea here is that you define filter kernels which adapt to the local image content. And since these shapes can be very different, they were called amoebas, like, say, what you have in nature. So the structure function in this case is defined as follows. It's points, a set of points where, say, a certain amoeba distance function is smaller than a given radius. And so this is where things become dependent on the image, because this amoeba distance is dependent on the image. Here an example of the result. So on top left, you have an input image. And then first, you have to compute a pilot image, where there are, in this case, there are two ways to do it. You can use a Gaussian filter, top middle, or you can use this amoeba mean filter, where, say, this amoeba filter depends on the image itself. And so you see that the pilot images are very different. And then below you see two results. Bottom left is the amoeba mean image with the Gaussian pilot, and right you see it with the amoeba pilot. And so you see that because of this amoeba pilot function, it captures better certain, say, input properties. Like if you look at the hand, you see that the Gaussian case blurs it more than, say, the amoeba pilot, which is really adapting to the image much better. Okay, so far for, say, the adaptive case. Now we look at extending it to different function spaces. So first, the vector valued case. Essentially, if you have a vector valued image, the problem becomes how to order those function values. So remember, in the binary and grayscale case, we had an ordering for the binary case is the ordering of sets, inclusion of sets. For the grayscale case, it's just the linear ordering of function values, since it's just, say, the real numbers where we have the ordering. But if you have a vector, how do you compare vectors? How can you do ordering of vectors and later on tensors? This is really the problem. Now I will confine myself to a specific vector valued image, which is a color image. And this slide presents the problem. So if you have, say, two images, where the orange one with the RGB values and the blue one with the RGB values, you can define a join or supremum and a meet or infimum. But what you see is that you get very different colors. So you get new colors in the image. And this is really what people consider to be a problem, the so-called false color problem. So the real problem is if you do this, say, a comparison by just working on the individual RGB components and then taking the supremum or infimum, you get new colors in the image, as you can see here. So you have orange and blue, but you get pink, and sometimes you get gray, where there was no gray in the input images. This is called the false color problem. Here's an example where you see what happens for a real input image. So if you define the dilation in this RGB basis, using the definitions I just presented, you get all kinds of new colors in the image, which is a bit strange, or at least non-intuitive. How to solve this? Well, many people have worked on it and many solutions have been proposed. I'm now presenting a solution which was developed by my former PhD student, Jasper van der Gronden, who came up with the following idea. If it is the case that, say, results depend on, say, a fixed color basis like RGB, why not construct, say, a set of color bases? So not just a given one, like the one on the left, but simply consider all the rotations of this color basis. Of course, a finite number of rotations in practice. Nevertheless, you consider now a group of rotations of the color space and looking at invariance under this group. So it's in some sense also an extension of, or an application of group morphology. And this collection of rotated basis functions is called a frame. So again, the first paper, journal paper on this was in IEEE Transaction on Image Processing. So here is how it works. You take an input image, top left, and then you lift it to the frame representation. So you get not a single image, but many images which are generated by these rotations of the color space. Then in this extended representation, you filter the dilation, erosion, any other filter you like. And then you have to go back to an image, and then the theory says that there is no unique way to go back. So what we do is a least square projection, and then you get the results. So here's again the case of the bird which we saw before. On the left, the dilation in the RGB basis with the false colors. On the right, the dilation in the U invariant frame. So we consider here only rotations of the U's. Of course, you can also extend the invariance to the full color space, but here we only consider the U's. And you still have the colors as they were in the input image. So I come to my final example. This is tensor valid images. Now, before going to the morphological operations, let me just give a few slides about how you can get tensor images. This is one way to achieve this, which is called diffusion tensor imaging, which is widely used in biomedical imaging and neuroscience. So this is also a topic my group has been working on. Just a few slides for introduction. So what you can obtained by a magnetic resonance imaging scanner is data which allow you to, in each point, measure the directions of water flow. And these directions give essentially a matrix of diffusion coefficients, which now depend on the direction. So what you get is the diffusion tensor, which you can visualize by this ellipsoid. So if you look again in any point of the input image, 3D in this case, you get this matrix or tensor, which you can diagonalize, and you get the major axes of this ellipsoid. And so the largest one, the largest eigenvalue in this direction, gives you the main direction of water flow. So this picture has colored, say, the diffusivities with these colors. So red is left, right, green is bottom to top, and blue is orthogonal to the image plane. Now this is still 2D, so you can also try to now follow, starting in a given point, where the main, say, direction of water flow will lead you. And then you can compute fiber tracts. So again, you start in a point, you follow the main direction of water flow to the next, say, volume point, next voxel. And so you continue following, say, the main direction of water flow or diffusion. And then you can compute these fibers. So these are in the corpus callosum, which is a central part in the brain connecting left and right part. It has many fibers. And you can also color these fibers by their anisotropy direction, so indicating what the main direction of flow is. By the way, we also did some work on, say, enhancing this representation. This is just for black and white images by so-called halos. So each fiber is projected on the background, say, on a black background or white background, so that it's more emphasized. And then you get a very good insight in how the fiber bundles are running in the brain. Okay, back to morphology. So again, this is a complicated exercise. I will restrict myself to saying that essentially do the same as for, say, the vector case, namely trying to compute a frame. So again, if you look at two representation of a tensor, and you compute, say, the minimum component-wise, you get a result which is not very intuitive. While if you look at our method, it can compute results which still look like a real tensor. So again, we construct invariant operators under rotations of, say, the basic tensor basis. So it's like in the vector case, both for example, for meet and join. So here you get inputs and then a meet, and it's the same as the joining the meet and then do the translation or the transformation in this general, say, tensor domain. So as you can see here, we now have a rotation invariant frame, which we can construct like in the vector case, and then we do the same setup. So we have a tensor image, top left. We do a lift to the tensor, to the frame representation, excuse me. So you get all these rotated versions, you filter, and then you project back by these squares. Again, this was work of Jasper van der Gronde. So a final example, and here's a tensor which is not constructed from, say, the diffusion tensor imaging, but just from an image, the so-called structured tensor. So if you have a grayscale image, you can look at the directional derivative in all directions, A, and you can work out this formula, and what comes out is a tensor, T of x, and this tensor is called the structured tensor. And so in the images, you see an example of applying our, let's say, frame-based approach. On the left, the original image. On the middle, you have the gradient magnitude, which has zeros and at the crossings. And on the right, you have the result after we filter, in our case by a closing, but in the frame representation, using the setup I just described. And then what you see is that, say, the 0 responses are filled in by this filter. So you get rid of all these gaps, but the result is still sharp in the sense that the edges are still thin. So I've come to the end of my talk. So let me summarize what I have been discussing. We started with standard mathematical morphology using the invariance on the translations of the image space. And then we generalized this to other transformation groups, leading to group morphology. And we have seen many different cases, abelian or commutative groups or non-abelian groups. Then we looked at adaptive morphology, where you have really to be careful to distinguish between location adaptivity, where only the structuring element or function depends on position, or the case where, say, you have an independence on the input image, and this input adaptivity is much more complicated, and you have to be careful. So you have to use these pilot images in this approach. Then we looked at vector images, for example, color images, where, say, these false colors are contrary to intuition. And using frames, you get more natural results. Of course, what is natural and non-natural is always up to debate. But at least if you start from assumptions that you want to avoid these false colors, then the frame-based approach is one way to solve this problem. And finally, we mentioned tensor morphology as an extension of vector morphology, where, again, you construct rotation invariant frames from certain tensor bases. So I've come to the end of my talk. I thank you for your attention, and I would be happy to answer any questions.
Okay, thank you very much, Jos, for your very interesting talk. I would like to ask you maybe one question, because we do not have much time. As far as I remember, the 19th, it was the time of very intensive research in the area of mathematical morphology, with the conference, many conferences organized, devoted to this subject. And I remember you also organized in the Netherlands the conference on mathematical morphology. And how you consider now, what are the main direction where people which are interested in the mathematical morphology are working on now? What is the most important topics of research in mathematical morphology now? How do you consider?
Okay, I think there are two answers to this. On the one hand, I think morphology has become applied to many different application domains. Initially, I think there was a lot of theoretical research in which actually I was involved myself as well. People have really teamed up with, say, researchers. For example, in the medical domain, there are many cases where, say, morphology is used. I showed only one example of this diffusion tensor case, but I've had projects also with medical colleagues where we looked at, say, sharpening images or extracting, say, blood vessels or all kinds of other, say, operations on medical images. This is only one application. There are other applications in astronomy, material science. So I think this is important. It's really very good to see that, you know, the framework of morphology is applied in practice. On the theoretical side, I think there are also still interesting developments. I think from the 90s, one particular one is the so-called connected filters. These are filters which try to keep or remove certain, say, connected elements of the image. And there has been a lot of research on these connected or hyperconnected filters. Then I would say there's still also a lot of research on effective algorithms, also for these more complicated, say, operations. So this is, I think, still a very active field of research. And well, as you mentioned, the conferences which started in the 90s, they still exist. Every 2 to 3 years. Actually, we organized it twice in the Netherlands, once in Amsterdam, once in Groningen. And so I think the field is still quite active.
Okay, thank you very much, Jos. I would like also, maybe other people listening your presentation would like to ask questions. Not much, but maybe one additional questions, please. Okay, no, I think no other questions. Jos, I would like to thank you very much once more for your very interesting talk on mathematical morphology, and I was also very happy to see you participating at our conference. Thank you very much.
You're welcome.
So, colleagues, I think we need to proceed, and Mr. Chairman, you may announce the next speaker if we have no questions. Because, well, participants, please, those who are in Zoom, you may ask questions just holding your hand or just open your mic and just ask questions. Now, I think next speaker will come because we are a bit out of schedule now. Thank you.
Okay, thank you very much, Alexei. We now come to our next plenary presentation. I would like to announce the title of presentation of Professor Frédéric Leymarié, Towards Creative Robots and Artificial Intelligence with a Human Touch. I do not know whether oh, Frédéric, I see you. Nice to see you.
Good to see you again.
Frédéric, I would like to make a short introduction before your talk.
Thank you.
Because I'm very glad to introduce Professor Frédéric Leymarié, who is working from 2004 at the computing department at Goldsmiths of the University of London. And the areas of interest of Frédéric, I've taken them from the website, computer vision and computer graphics, artificial intelligence, machine learning and creativity, artificial skillful robots, interactive platform for biosciences, intersections of visual art and lives performances with computing, perception, and robots. So a broad area of research interest. I would like to say that Frédéric got his PhD in 2003 from the Brown University in the United States of America with the title Three-Dimensional Shape Representation via Shock Flows. And I would like to, as far as I remember, you graduated McGill University, right, in Canada. And because I remember we met many years ago, it was about 30 years ago in the Center of Mathematical Morphology in France. That time you were still probably just finished your master study. Yes, and
Yes.
Your scientific career was still ahead. Yes, and now you are full professor at the University of London. But what I would like to say, because I teach also a course on basics of image processing, and with students we still study your paper, which was published when you were a master student on distance transform. It's a very good paper, and we study it with our students. So I would like now to give the floor to Professor Leymarié for his very interesting talk on creative robots and artificial intelligence with a human touch. Please, Frederick.
Thank you very much. It's a pleasure to meet again, although it's online, virtual. I remember our meetings in Fontainebleau with Professor Serra, and this was a great time indeed. So thanks again for having me. Let me start and share my screen. Hopefully that's going to work. Right, okay. So I think you should see my screen now.
We see your presentation. Mm-hmm.
Okay, so yes, I will talk about topics that are different from previous talk. I would like to thank Professor Rodrink. We met not so long ago at the PhD defense, and I follow the field of morphology as much as I can and still use that part of image processing in some of my work. Is actually in some of the work I present, underlying it, morphology plays a role. So I would like also to add, I added a subtitle. So this is part of a long-term research program, which I entitled Art Machine Intelligence, and it's really about the intersection of all these fields. So let me move on. How do these three areas might come together? Art, let's say a little bit about art. So I take, let's say, a view on what we mean by art. I'm mainly here speaking of art as an activity where we produce artifacts. I'm not considering art that goes into art galleries or the issues of social impacts, the marketing of art. So all these areas are very interesting, but at a different level of what I'm considering. So I'm considering really the basics of art, what we mean by art when we create different artifacts. Here I put a few keywords to sort of emphasize aspects of art that are relevant to my discussion. So you see the words of creativity, coming up with new concepts. There's a side of actions, and this relates to how we use our body in creating these artifacts, and I'll come back to that. There's a notion of skills. You can get better and better. You can gain expertise in activities of creating art. There's issues of communication. Art is to be observed and appreciated by others. You can communicate ideas, concepts via artistic activities. You can think of sketches, diagrams. So I take a sort of a broad view of art here. There's notion of aesthetics. What makes an outcome, an artistic outcome, interesting, or we would say beautiful, skillful. There are ideas from the world of art over many centuries that I think are relevant to AI in general and computer vision in particular. This notion of representations, how we represent concepts. And art is part of everybody's experience in learning about the world. I'll say a little more about that in a few seconds. So the other main topics is what I call machines. Machines really starts with way back in our history, even prehistory, with the concept of tools. So it starts there, and it progresses through time, and really machines become extensions of our body. So I'll just put that out there, and we'll come back to it. And in terms of intelligence, what I want to focus on here is those aspects of intelligence that differentiate us from other species. So all species have some notion of intelligence. We could discuss that. It's an ongoing discussion in general in science. But what I want to try to emphasize here is, can we focus perhaps on what makes us different, what we can identify as intelligent actions that are different from other species. So the discussion also is in terms of historical view on the evolution of what we nowadays call AI, or artificial intelligence. Here I put a starting point in 1950 with a famous paper by Alan Turing on the notion of imitation, so-called Turing tests, or versions of the Turing test, what he called the imitation game. And really here, Alan Turing is proposing the idea that in order to develop machines that show signs of intelligence, we can consider a concept of imitation. And this is, again, the so-called famous Turing test. And I don't want to go into too much detail, but that's something we could return to later. A few years later, we have actually the proposal of what artificial intelligence will become. So you have a famous meeting in the east coast of the USA, in Dartmouth College, and it is proposed there that AI, or artificial intelligence, should be the field of study where we basically simulate aspects of intelligence, here meaning human intelligence, that we have some understanding of, using the machines of the day, which is the beginning of computers. So here's a slightly different view on how to see artificial intelligence. The idea here is, let's simulate aspects of human intelligence, or potentially other animal intelligence that we have some understanding of, and sort of verify that understanding via a machine, which would be typically a computer. So what we can consider nowadays is what I called AMI, art, machines, and intelligence, their intersection. And what I'm proposing here is that aspects of art can be combined, such as creativity, practice, the practice of art, artistic activities. The notion of expertise can be combined with machines, their design, engineering, their control, their applications. I'll return to these topics later on, and can come together to better understand what human intelligence is. So this is a sort of complementary view on the previous views, where by combining these fields, we might be able to actually understand what intelligence is made of, or at least some elements, some basics of aspects of human intelligence. So that's sort of the agenda. Again, it's my long-term research program. And I want to specialize it today in the context of a particular activity in the world of art, a very important one, which goes back all the way to the origin of arts, which we can date, by the way, to tens of thousands of years ago, the activity of drawing. So why drawing? Drawing is one of the main activities humans use to express creativity. As it will become clearer later with some examples, it is a process-based activity. That's sort of an engineering view on the activity of art. It is meant to be appreciated, what I call reflexive. So this is bringing in notions from psychology. Why do we observe art, and how can we distinguish features and give notions of appreciation, quality to a piece of art? So this calls in the field of perception in particular. In the context of my research agenda, I propose that this is a very interesting activity where we have lots of examples and knowledge, which gives us a window into our mind, opens up new possibilities to study, again, human intelligence. Also very interestingly here is that of all the art practices that we could study, this is one of those that is shared by everybody. So essentially, if we look at young children, the activity of drawing is an activity practiced by all, typically. I mean, it would be very unusual that we don't let a child explore concepts via drawing. So that's typically something we've all experienced. We can directly relate to the activity of drawing. It is also an activity that we use in youth from a very early age to build up representations of the world. So there are very interesting studies, especially in the world of in the field of psychology, studying how children evolve their representations of the world, of concepts, and this can be studied and observed by how their drawings evolve through first years of life. So there's a good source of knowledge that we have used, in fact, in some of our research. It's an activity which is culturally bound, so different than later, if we consider later periods in the life of a person, their drawing practice will start evolving, influenced by culture. So this is a topic we could also consider here. I'm not going to talk too much about it. It is also importantly for my discussion in our research program, it is an activity which is clearly performed by an articulated body. So I just want to give you rapidly some examples of very different types of drawing, just to sort of lay out the field of what is out there that we could consider to study. So here's a sketch by a famous Spanish artist, Pablo Gargalo, where we have an exploration. So typically a sketch in the context of an artistic studio is a way to explore a possible concept that later will be refined into a final piece, could be a painting or a more precise drawing. And here we see all kinds of lines. If we were to study them in small region individually at the pixel level, it's not very sensical, but if we look at it as a global view, we get very strong information. So that poses then the question, how does the human brain process such images? And with the art practice, we can actually study that by the way of how is it produced. Another example, so this is a technique sometimes called line of action. You see a main line being drawn through the body here. This is actually the first line that is put on paper, so-called line of action, and that determines the essential pose, attitude of a character. It's sometimes referred to also as part of what's called gesture drawing. So then you have these rapid movements here to flesh out the body. This line of action is a technique that has been employed in particular in the world of animation, was made popular by Disney Studios since the 1930s, where you would draw a few of these lines on blank set of piece of paper, and you would therefore characterize how is the pose of a character changing over many frames towards selecting how a character is going to move into the final animation. So again, another very interesting technique that we find in the world of art that has strong features. We recognize immediately what it is about. Here's a completely different technique, also quite old, actually much older. You find such description of objects via primitives. Here's the notion of volumetric representations as primitives, to assemble essentially a complex object into its parts. And this was already familiar to Renaissance people, such as Leonardo, for example, or even before him. So again, a different technique which will evoke to some of us notions that have been explored in computer vision for representing objects, for example. Final example here from the world of art, just again to sort of try to convince you that there's a lot of richness to get from centuries of evolution of art techniques. So here is the problem is representing movement, different poses again in one canvas. And this is illustrations taken from a course given at the Pratt Institute in New York. As an example, you would use these kinds of representations, for example, for setting a scenario for a stage performance. So different techniques. People who are familiar with mocap, motion capture systems, will see a connection here, I think. So in the rest of my talk, I want to mainly give you some concrete research examples. And I'm going to cover two main projects. And to do that, I'm first going to set a methodology that we have followed in these projects and a few others. So the way we proceed is first we select an area of particular art practice, and then we enter into discussion with experts. Here the experts will be artists who are experts in the particular type of practice. In a series of discussion with artists, we then seek to take the point of view of an engineer and try to distinguish different processes that the artist goes through repetitively when they think and then put on paper an artifact. So this will vary what you come up with in terms of a representation of the thinking and the process. It will vary with the given artist and the given type of art practice. At that stage, we try to isolate different aspects of these processes in what I called here primitives. And you can imagine building a sort of block diagram of relationship between these different primitives. I'll give you an example shortly. We're then ready to have computational models put in place, and we will test them, implement them, refine them, the usual iterative mode of testing methods via computations. Once we start reaching good results or interesting results, which reflect well on how a human would produce the same type of artifact, we then evolve our computational models towards embodied systems, typically into robotics, into different types of robots. And we say that at that point, once our robotic systems are giving good artifacts, we have ways to test the ground truth of our initial program, which is, do we have a good model for how the human produces such artifacts, and can we verify that we have a deeper understanding of how the human achieves such artifacts. So, sorry, I went a bit fast here, but I want to say just a little more about the robotic side of our agenda here. So why go all the way to robots? Why not just stop with computational models? Well, with robots, we actually push ourselves a little more. And there's also certain aspects of the artistic creation which are captured with robots, which are not easily simulated, if you want, with purely computational models. So with robots, we can actually also put ourselves in theatrical performance settings And this is obviously of importance for artists themselves who want to use such contraption in their practice. I'll give you some examples. But also you can think of the world of psychology when we want to do testings on those models that we're embodying in robots and comparing them with how humans, observers this time, react to those artistic applications. So it has an impact on the psychology side, and I can point you towards recent papers on that front later on. It introduced, having robots implementation introduced constraints that are not necessarily considered when you have a purely computational model. You have to actually deal with a body, the body of the robot. You have to control it. You have to have sequences of movements. The body, if you want, can get in the way. If you think of a robot which is drawing or painting, all considerations would not be really there as constraints if you're in the world of computations only. Because you're driving a physical object, the body of the robot, there will be a lot of uncertainties due to the architecture of the robot and its dynamics, which again are part of the construction of the robot and not necessarily easy to simulate or understand it from a purely computational viewpoint. So, whoops, hopefully that, I'm going backward now, yes. Hopefully that explains better why we go all the way to robotic implementations. There is a sort of philosophical also point of view here. I will not spend too much time here, but if you consider viewpoints today that are considered in the field of AI, there is this group within the AI community that considers that intelligence should be studied via so-called embodiment. And then there's a sort of a contrarian viewpoint, which says that the computational viewpoint is sufficient, a computational only viewpoint. So here we're following the embodiment hypothesis that intelligence, I'll summarize here very shortly, intelligence is in part due and constrained by our body capacities in using tools, sensing the world, aiming to interfere with it. And here's an example from a famous artist, how the body plays an important role. It's the body active in space. So it is really a dynamic system. Jackson Pollock from around 1950s, and the famous practice he popularized called action art. So my first project I want to briefly cover goes back to about 10 years ago. It's a collaboration with artist Patrick Tresset. Patrick was active, had already had a career as an artist, but also had been educated in programming. And we met when I came to London. And eventually, after a few years, we were able to set up a structure with funding. And we studied portraiture. So how Patrick was doing portraits of people. And we went through the process of understanding how he thinks, how he proceeds from an image, from looking at someone towards describing the essence of sort of a skeleton of a face that you see here at the top as a sketch here. What other parts of his actions are important? Visual perception, where we have constant feedback on the image of the face. Issues of moving the body in particular ways to do drawing actions. So you can imagine that a given artist looking at the same person, each time they do a portrait, they will go through different dynamic processes, and they will never really do exactly the same portraiture. And then in our discussion, it became clear that Patrick was thinking in terms of also higher level descriptions of the face, what we call here mental imagery, so-called schemata, which comes from the field of art. There's a notion of experience. So a given artist will be influenced by other artists by their own education. So we wanted to put all this together in a project and study these aspects as sort of primitives and try to come up with systems that would duplicate this way of thinking and acting. This is an early result. That's a purely computational model, which was implementing our view at the time of how Patrick goes about portraiture. And you will notice here, if you look at the details, that the drawing gestures are very repetitive. This is the sign of a computational model or purely machine model, which is approximating what the type of sketches Patrick was doing, but doesn't have the same qualities. So we were trying to understand what distinguishes a purely computational model from a human performance. And we had the sort of eureka moment of thinking that perhaps if we move to an embodied version of our modeling, we would approach better how the human creates such artifacts. So what you see here is our first first version of an embodiment of the previous computational model that we had explored for a few years. We called at the time that system ICON for the automated iconograph. Later, this system was called again Paul the Robot. So if you look it up on the web, you'll see Patrick Tresset's studio, and you'll see his different versions of such robots called Paul the Robot. It's a series. And what it is it's articulated arm holding a pen. It has a wrist. It has also a camera eye that can rotate around and find faces. And that camera eventually we used in looking at the drawing and influencing the drawing. So here's an example of that system. It captures a face of a person, and now it's observing the drawing while it's drawing it. Under the table here, so Paul the Robot is this eye, camera eye, this arm drawing, manipulating here a pen, and under the table you have the sort of brain or rest of the nervous system, which is the computer. These drawings typically take anywhere between 15 to 20 minutes. There's a performance aspect to it. There's attention of the person, which is important in the performance here. So they experience a portrait rendering which is similar to what they would experience with a human. So what happened with this project, we worked for a few years together. Our last research contribution is a journal article from 2013 in the Journal of Computer Graphics, where we had our first description of using visual feedback, that is using the camera eye not only to just capture a face and use some of its features to drive the robot performance, but also the camera eye was used to look at the qualities of the drawing as we make it, and the robot could adapt, refine the drawing gestures. So there is a journal article explaining this. Patrick then went back to the world of art and has been very active since. We can look him up. Currently, his studio is based in Brussels, and he typically has exhibitions of his new versions of robots around the world. So here's a more recent example where he's using some machine learning technique in combination this time. So he has refined the power, if you want, of his robotic model, where here the robot is considering a sketch that has been drawn by Patrick, and then inspired by that sketch will do a augmented version using the style that has been developed by Patrick via these robots. So this is sort of an early example of a collaboration, human-machine collaboration in that world of robotic portraiture. So I said that I would cover two main projects, so I will now, in the next few minutes, cover the second project. So what happened after 2013 is around that time, I was lucky enough to meet another brilliant artist and programmer, Daniel Berrio, this time, an Italian fellow. And we started around late 2014 to have discussions. The art practice that Daniel Berrio is an expert of is so-called graffiti art. I'll give you some examples of what we mean by graffiti art in a few seconds. And the research agenda here was to go beyond what we had done with Patrick. So with Patrick, we had sort of explored the methodology, the full methodology of thinking of what are the processes that an artist considers. Can we build a computational model, verify it? Can we import it on a robotic assistant? So here we're going to go through all those steps, but we're going to refine the research agenda by focusing on movement. What is the influence of movement on the quality of the traces that we produce? This was a question we put forward at the beginning of our research. At the time, we knew already from research, especially coming from the world of cognitive science, that there were indications that as an observer, you appreciate artifacts, especially in the world of drawings and calligraphy, by recovering the movement, the likely movement used to produce the different traces, the different strokes of that artifact. And this has been an hypothesis that's been around since at least the 1990s. So we were influenced by these results. And just to try to convince you why this might make sense, here's an example of a calligraphic artifact. And if you start asking, so if you now put yourself in a psychology experiment, you start asking different observers, how was this produced? They will come up with descriptions of traces and even the sequencing, which will be fairly homogeneous across subjects. So it looks like we are able to figure out how was this produced. It goes beyond that. So in fact, in terms of aesthetics now, the fact that we understand how a piece of art is produced by likely movements gives us pleasure. And this is, again, part of the hypothesis as it's described in the world of cognitive science. We could discuss that further. So we took that as a starting point. We established along the years different collaborations. I want to briefly highlight them. With UIIP in Switzerland, we work with Sylvain Callinon, an expert in robotics and in applying machine learning to robots, especially learning from examples, that is, learning from humans. At Polytechnique in Montreal, we work with Professor Régent Plamondon, who's a pioneer and expert in what's called graphonomy, which is the science of studying how humans write. Initially, that was the main purpose. It has evolved now in all kinds of activities related to writing. So essentially, drawing would be part of that field, and that is why we were interested in working with him. Johan Wagemans, a psychologist at Leuven University, we've collaborated with on the psychology side. Also, one of his ex-student, Rebecca Chamberlain, who is now at Goldsmith. And more recently, we work with some researchers, Paul Asante, Jose Echeverria at Adobe Research. On results, I won't really show much now because I'm running out of time, but this is evolving the work I will illustrate next from one-dimensional traces to 2D traces of letters, in particular fonts. So the next few minutes to end my talk, I will exemplify the same method we saw illustrated for portraiture in the context of graffiti. What is graffiti? I consider it as a modern form of calligraphy, the very ancient art of calligraphy. Graffiti is made of very rapid gestures over large areas using all kinds of tools, spray painting, for example, brushes, different materials, different surface types. why focus on this particular art? Well, again, our focus is to understand the dynamics of movements and how it influences the quality of the traces. So we think this is an excellent modern area practice to explore. Here you see Daniel Berrio and some of the art that he can produce. So these are very large canvas, beautifully done. And one thing that's quite extraordinary is to see it being done. It's they do these things very, very rapidly. The expertise level is very high. I cannot go into a lot of details, of course, time is limited, but underlying the particular processes we try to model, we have focused in particular on so-called sigma log normal model. So this is influenced by Professor Plamondon at École Polytechnique. And this is one of the popular mathematical model that is believed to be a good way to represent how humans use speed when they do writing traces. What you see here, in fact, is, I'll explain a little bit more. You have a simple drawing gesture made of two main traces with 3 targets. So a start, an intermediate target, final target. And you see here a particular way of doing a gesture which lay a trace trying to reach these targets. What you see here on the right-hand side is the sigma log normal, which indicates how the speed is varying. There's more to say about that model. It's been studied over decades now, and why it might be a good model to represent how humans move their limbs. I won't go into that, but there's lots of literature if you're interested. So what we observe here is that with the same targets, we have 3 different, very different renderings of reaching these same targets. And the only difference here is how we play with the sigma log normal, which represents the 2 main movements. So movements from the start to the middle target and middle to the end target. So each of these Gaussian-like, so sigma log normal is actually an asymmetric version of a Gaussian. You can think of it that way to summarize. How you distinguish the traces can be understood as how the kinematics is performed via this model. And here's an example with a more complex set of traces. This would be a typical so-called tag or signature in graffiti. And you have a number of gestures that have been produced, and we're capturing a particular rendering with the targets shown in red here, using sequences of these sigma log normals. So that's the underlying main computational model to understand movements here. So we have, I'm going very briefly, I can indicate a website where you have literature, a series of papers if you're interested in the details. But what we've put in place now is the computational model. We can observe how a human expert produces such graffiti art. We end up with, we can use image processing to retrieve number of targets from the human production. And then we can start recovering the kinematics of how it was likely produced as an observer might do using the sigma log normal model. And so finally, with all this technology, we can actually test and embed these models in robotic systems. So here's a virtual simulation of animating such robots, just to give you a feel. Here's an actual robot. So this is a Calinon at UIIP. It's a robot which can interact with humans, in fact, so a very interesting one for collaborative work. More recently, we keep refining the models we have access to. So here's just a few papers to give you a feel for that. In particular, more recently we've explored how to embed such an understanding of the kinematics with so-called recurrent neural networks, RNNs. So basically the neural network here is there to capture the different parameters that we need to set to perform a particular rendering. And then what you have is with the neural network is that you can start render with the same targets, many different versions, essentially combining a set of targets for different potential artists. So the kinematics of different artists can be, if you want, captured by the neural network during a training session. And this can then be used to do rapidly many versions of the rendering. So where next? I'm reaching soon my conclusion. Where next with this research agenda? So here's a few topics we're thinking, and some of them we've started to explore. So we are looking at how to relate image data that could be used in this context and studied in this context. So the challenge here is to map image information or intensive information into strokes. How do you go from a painting, let's say, so a very dense field or image, and recover these gestures that we've studied in the context of calligraphy. So in calligraphy or graffiti, typically the strokes are very obvious, very present, and the image processing that we can use that exists is sufficient to recover these. But if you consider image-like data or painting-like data, this remains a challenge. So this is part of our current research agenda. An area we ourselves have not explored, but others have started to explore is the sense of touch. So that's missing from our current model, and I think that's also a very interesting area to combine here, haptics and sense of touch, and how pressure influence gives you another kind of feedback in the rendering of these artifacts. Human-machine collaborative modes of explorations we've started to study, but that's an open area also to engage with. So this is more in the application domain of this kind of research. And of course, we plan to continue to work with different artists in order to try to unlock different aspects of intelligence. My last slide, sort of more of a general pitch. I hope you will find this convincing with the few examples also I've given you. From an historical point of view, if we look all the way back in the past, all the way to even prehistory, we see that art and machines, back then it would be simple tools, have actually co-evolved together. So we've actually started to design tools and then later machines in the context of art practice. Not just art, but that has been one of the drivers. Our history is one of continuously extending our cognitive horizons. So I actually believe that, or I would pitch the idea that this kind of research is actually also helping in exploring other ways of doing art or performing art. And this is yet another way to expand our so-called cognitive horizon, which is a particular view on what intelligence is about. And we could have a long discussion here on what we mean in this sense. And final point, art is a distinctive aspect of human intelligence. It is one of these aspects which is very particular to the human species. There are very little examples of anything artistic being done in other species. You can see some species, birds, for example, who have some notions of art, apparently, but they're very limited. So this is one of our distinguishing feature, art. It stands at the roots of many other distinguishing features if we consider what distinguishes us from other species. Writing, for example. Writing emerges long after the origins of art and is a direct outcome of art. So if you think of hieroglyph, symbols, in the context of semiotics, architecture, in terms of drawing, sketching, engineering, even mathematics in times of the Greeks, for example. And I believe, or I would like to convince you that it deserves a place of choice in the future of AI and robotics. Thank you, and there might be a minute or two for one or two questions.
Okay. Dear Frederic, thank you very much for your very interesting presentation. Yes, we're already out of schedule. Yes,
Sorry about that.
Yeah, but I would like to ask you one question also. Maybe somebody also will ask. Now there is a lot of attention and application of these machine learning technologies and especially deep learning technologies. But as far as I understood, you do not use these methods in your project. At least your robot drawing project was it's maybe a bit early, 1930 or 2013. You did the robot drawing projects, but now do you also combine these machine learning approaches in your projects or not?
Yes, in fact, yes. So there were a few slides where we mentioned some work with machine learning. So yes, we've engaged with it in the last few years. You're right that in the first project I presented, we were not considering machine learning at the time. Of course, back then, 2010, 2013, it's still not, machine learning is not present as it is nowadays. Really starts to emerge around 2015, let's say, and influence many other fields. But yes, we've engaged with it, and we're doing more in the combination of machine learning and some of the work we do. So for example, the work with Sylvain Calinon at IDIAP includes some machine learning approaches. We've done some work on using recurrent neural networks, which I briefly mentioned in one of my slides. Essentially here we are trying to capture a notion of memory. So we use the neural network approach to embed memory of how different artists use differently their movements. So it's part of the kinematic modeling. So essentially the idea is that then what you can do is you can have, let's say, an agenda, a different set of targets. You're going to draw a particular letter, let's say. And the neural network is able to render these targets with the style of many different artists because it has been trained to capture the kinematics that characterize the style of each of them. So of course, the assumption here it goes back to the hypothesis that the kinematics, how you actually move when you draw, is fundamental to the quality of the trace that is produced.
Okay.
And that's an inference from the world of
okay.
But these are early days. I also agree with
Frederic,
we
do not have time because the next session will be in 3 minutes. I would like to thank you very much for your acceptance to our invitation to participate in our conference. Thanks a lot. But I hope to see you also at this panel discussion. You also agreed to participate. Yes. Thank you very much once more.
Thank you, Frederic. Yes.
Goodbye.
Bye-bye.
Thank you.
So, yes, we will hope to see you, dear Frederic, on Friday because we will have a panel session which will be about AI and ethic issues and something else. So we'll see. You're brave because we have luck with London in 2 hours, so you need to stand up earlier to be with the other panelists. But still, so thank you again. Now I would like to announce that we have a very small breathing break, and we will come back in just 12:00, and we will have the first session A1 in our conference. So see you after the break. Thank you. So, dear ladies and gentlemen, we are now coming back to our studio. So I hope that you already take 1 or 2 breaths, because this break was, well, too small, because, well, our last presenter was a little bit out of schedule, but I hope that you enjoyed with the speech. Now we will start our session, and the session chairman should be Professor Viktor Krasnoproshin. So unfortunately, I will be a chairman, not him. But anyway, I hope all of our presentations and all of our presenters are here. Now I would like to give a floor to the first presenter. So the presenter who will, let's say, present the paper report called Paralyzing by Smart Tallinn by Sergey Sushko, Alexander Cheremys, and Svetlana Reznikova. So please, colleagues, you have a floor now. You may start your screen, share the screen, and go with your presentation. Thank you.
Thank you very much. Can you see my
yes, exactly. You may proceed.
Okay, thank you very much. My name is Sergey Sushko. Me and Dr. Alexander Cheremys and Svetlana Reznikova prepared a presentation for you. And all of us, we are representing of National Academy of Science of Ukraine. So I'm very happy to be for the first time in this conference and share with you my investigations. My report will be dedicated to the software optimization topic. It's quite a big task. And as you can see on my title, it's Paralyzing by Smart Tallinn. So Smart Tallinn is a new method proposed by our team. And I'll describe it with you during this presentation. So let's make short focus on optimization issues. So first of all, where it can be applied. Actually, it can be applied everywhere for some mobile application, for some embedded servers, grid, and so on. So in any case, optimization gives us some new opportunity, like more functionality, more features, or some less power consumption and less cost of holding of the servers. So it's every time it makes some benefits. From the other side, it's manual optimization. It's a long and quite tedious way, and it requires a lot of skills from software engineers to do it. And actually, it's not is done in best way. So in common, several stages of optimization can be highlighted. Top one is algorithm optimization. It's usually what mathematicians and sometimes a software engineer do. And it's the highest level. So it's a global approach, global algorithm, which should be realized in software source code. So second one is like microcode optimization. It's regarding the some usage of commands, sequence of it, and like a better representation for the compiler. And the last one, it's microcode optimization. It's actually what CPU will have after compilation. My scope is about second stage. It's optimization of command sequence. Actually, it's quite optimistic because we can change the code in different ways and optimize it somehow, and again use it with existing compilers. So this way allows us not only to use some specific feature, but it allows to be hardware and compiler independent. So we can change something and don't care about where it will be applied. So in common, we have let's say, a big problem of proper selection of optimization methods. So we can have a lot of methods which pointed with letter M, and some parameters of these methods with letter P. So, and for every part of code with index I, it can be some specific set of these methods and its parameters to obtain the best parameter which have to be optimized. For example, and usually it's computational time, but sometimes it's data memory size, program memory, energy consumption, and so on. So the big deal is to find these parameters in every specific algorithm, and not algorithm, even for program, for particular hardware. So if we are looking in the big list of existing some optimization methods, actually it's for speed up, it's usually optimization of computational loops, because it's quite small part of the program, but it's quite big impact on the total time execution. So as you can see, there are a lot of methods, and it's not the full list of it. And in some cases, it's one of them are better, another worse, and also some of the methods can be combined together. So as you understand, it's quite a big bunch of possible combinations and its parameters. So in my work, I was focused on parallelization. It's quite obvious that we have a lot of hardware units, computational, and CPU, and so on. So if we can divide some tasks onto smaller tasks, it's better to do it. It's obvious. And another quite promising method, named tiling. It's quite different way. It's not related to the cores, but it's divides iterative space of processing onto smaller blocks, which can be which reduce memory continuity, and also these tiles can be divided also in parallelization by several cores. For example, let's have a look on small example. It reproduces two-dimensional loops with I and J indexes from some restriction from 2 to 9 and from 1 till 9 also. And as you can see, it's blue rounds. It's actually some iterative points, and it's something should be computed. It doesn't matter what exactly. And gray rectangular, it's actually tiles. So for the first case, we divided 4 by 3. And for second one, we divided 3 by 3.
Excuse me. Pardon. So we can't see currently your screen. Could you share it again?
Sorry?
Yes. Your presentation or
no.
not? Okay. Well, so just camera, yes.
Oh, I show you my screen. Can you see it?
No, yet. Not yet.
Oh, so it's slide number 7.
that's okay actually. So because the oral presentation is also okay, but when you show in the formulas, of course it's better to see your screen. And our participants just claiming that they didn't see your screen. Yes, it was at the beginning, but now not.
Just a second. Okay, share screen. Screen number 2. And okay, can you see it now?
No, unfortunately.
Let me check again. Share screen.
Yes, now it's coming. It's loading. Yes, let's proceed with the slide number 7. Let's say, yeah.
Okay. some preliminary information. And let's
Yes,
continue.
that's okay.
Slide number 7.
Thank you.
Thank you for the information. So we have different talent division for 2 cases. And in common, it could be different because 4x3 and 3x3, as I understand, it could be thousands and even millions of iterations per loop. So it can be tens, thousands, or different particular values. And it's not clear which one we need to choose for better performance. But further, I will show you how to find out it properly. What's the main approach? The main approach is that we can use tiling methods, which is a source-to-source transformation. It means that line of this method doesn't produce any binary code. It produces some another source code. So in the first case, usually we do it this way. Like we have some source code, we compile it and execute the program. In this case, we inject some source code transformation before compilation, and then do our execution as always. So now several frameworks are available to do it. I use it Pluto, which has a lot of some blocks. Actually, source code transformation is only one of it, and another one is some additional stuff which allows to transform of the original source code to the polyhedral model, which Pluto works, and then after all the stuff, it produces another source code. So it looks quite ugly if you compare it with the previous one, but it does the work. So when we back to the previous slide about this tiling, what I made, I use it a lot of tiling blocks to the several, quite a lot of test programs, and just verify, does it make sense to change these tile sizes or it doesn't matter? So on these slides, you can see four pictures which represent of different types of time execution. For the horizontal lines in the slide, it's two tile sizes. And vertical axis is execution time. So as you can see, for every test, when we change in some range our tile sizes, we can obtain a completely different execution time. It means that if we want to use the maximum of speed up of the tiling method, we need to choose these tile sizes exactly very carefully, very particular for every test. For example, in the bad case, if we will be here, it means that we can speed up the program in tens of percents if we will change it slightly. And for different pictures also. And also what I would like to highlight, it's about the pattern of the every picture. So also, as you can see, it's completely different. There are some plateau like here, and can be some waves, some waterfalls, some hills. It depends on the particular test, and there are some pattern of it. So the big deal is to find some local minimum in every test, but we don't do it very simple because it's because of the picture, because of the pattern. So we need to choose such methods of the sorting of the better set of tiles, which allows us to find it over very different patterns. Also, I made some new metrics, which actually they show us how bad we can be in when we choose a bad style sizes in mean and in worst cases. So it means that for some tested, if it's in worst case, we can several times less actually more in time execution. And for some parallelizing, it's even be some huge values. So it's really the case when we need to choose these time sizes properly. And what I use it to do it, it's a particle swarm optimization method. It's quite known method of optimization. It has some iteration formula with for every particle, which is multi-agent of method, which can find the local minimum or maximum in the every possible field of search. So every particle has its own coordinates, which moves around some points and trying to find the local and global minimum. Why also this method it's good for our case? It's because it has actually some coefficients of social behavior. It means that every point knows about another point local minimum. And to show you how it works, I found some example of it, and you can see that some crosses trying to find some minimum which and tend to stick together. But for my case, it should be discrete particle optimization method because number of iteration of computational loops is obviously integer, and we have some integer grid which are for our case. So what we are proposed, it's actually smart tiling method. What does it have inside it? We have some initialization part, which starts before the every run, and two main blocks of it. It's actually discrete particle swarm optimization method, which trying to choose the proper size tiles, which determined by the formula on the slides. And also it uses existing tiling methods and parallelization together. Actually, parallelization can be omitted and it will still works. And how does it work? It proposes some initial points of particles in the proposed range, and check and uses tiling methods, which does the code, the compilation of the code, and measurement of the existing time, because we don't have any information till we actually measure the actual time. And if we meet some goals or reach the maximum iteration, we stop the algorithm, but in otherwise, we can to change the particle speed and actually again coordinates, and coordinates means that it's values of style sizes. And again, tiling methods will be applied with the different style sizes and measure time, and so on, so on, so on, and until we will have some required values or just some better values. So this is, as you can see, an iterative method. So it takes some time to reproduce and to measure all this stuff, but it's quite better because it's try to find some better values, not just one like default or some predefined. So to verify it, I made some measures of the source of the time and minimum values, and it usually requires less time after the, but it requires some time to obtain these values. And also I compared the original execution time aligned to 100%. It's white columns, and gray columns is applying an of tiling methods. And from the left side, it's like only single tile. From the right side, it's tile with parallelization. The darkest one is using of smart tiling method. And as you can see, if we had some 100% tiling, sometimes very significantly speed it up, sometimes not, and sometimes makes even worse. But when we are using smart tiling, it gives us a little bit more speed up against the original tiling method. So in this case, it's okay to use it, and just to remind that it requires some time to obtain this optimal values. And the same feature for the parallelization, even more, because it utilizes all the cores of the processors. So if algorithm is quite good on parallelization, it will be even better with smart tiling. So small conclusion. We have new methods which based on existing tiling method and discrete particle sum optimization method, which allows to optimize software more and produces better results than original tiling method. Okay, thank you, and I'm ready to answer all the questions.
Thank you for your presentation. So although we are out of schedule, I think it's good to ask some questions to you. So please, participants, do not be shy. So you can ask questions anyway. Okay, we have no questions now in Zoom or in Telegram chat, and in YouTube chat also we have no questions. I think we need to proceed. Well, anyway, so because we are now online, we are able to make shorter the big break. So it means be in frame of times, but feel free to present the full presentation of yours. I will not interrupt you, but still, so try to be in time. Well, our next presenter will give a report about graph-based recognition of high-level structures in transistor circuits. So please, you have a floor, Ludmila. Yeah, we see your camera, so now it's good to have a screen sharing also. Unfortunately, we can't hear you. Probably it's good to open the mic. So we're still in silence. Are you hearing us? Because we can't hear you. I think something with the mic. Yeah, you should unmute you. Now again, you mute. Please unmute yourself. So our colleagues will try to help you remotely. If not, probably please try to fix yourself. No, we can't hear you. This is because of your mic, probably. Well, I'm just want to probably Ludmila will try to solve it. I would like to announce that all papers which were submitted, which were reviewed, and which will be presented here in these 4 days will be published in proceedings and open license on the website, and it can be downloaded on the website. After the second revision, we will select and the selected papers also will be published in Springer's proceedings. So according to that rule, which were on our website also. So unfortunately, we can't hear you now. Let's go to the next presentation. Sergey Dvoyenko and Denis Pshenichny, A1.3, metric corrections of similarities based on orthogonal decomposition. So if you're ready, some of you, so any of you.
Yes,
Sergey,
I'm
Denis?
ready. Can you hear me?
Yes.
I asked to give me the screen from the previous report.
Okay. So?
Previous reporter need to close his demonstration.
Yes, but she's, well, yes, we have some.
Do you hear me?
Now, yes, now. So, yes.
Yes.
Sergey, please.
I would like to
hold on.
you
Be
a
with us.
topic, graph-based methods of recognition of high-level structures in transistor circuit. I am Lyudmila Cheremissina from United Institute of Information Problems. Так. Отлично. The considered problem is to decompile a flat transistor circuit. That is to convert it into a network of logical networks, of logical gates. First, the decompilation problem was used to accelerating simulation and verification of large VLCE system with many millions of transistors. Then it was used for re-engineering to change it with new basis technological and to detect triumphs and design changes. What we suggest? We suggested the program of decompilation and graph-based methods for solving some key tasks of decompilation program. Wherein we used the well-known tasks and graph methods, integrating and modifying them to process special types of large data in a short time. The proposed methods are implemented in C++, and some experiment on practical transistors systems show that it can treat it with large circuits in polynomial time in the number of transistors.
Unfortunately, we can't see your screen currently. So probably you stopped sharing it.
Well-defined static MOS circuits Отключилась демонстрация экрана. Да. Так. И что? Data representation. The source and resulting circuit netlists are presented in SPICE format. Each transistor in this format is specified by 4 labels. Correspond to drain, gate, source, and substrate of each transistor. The convenient and natural way to present such a transistor circuit is to use bipartite undirected graph as such graph. And in software presentation, such a graph is the array of nets.
Could you try to show your presentation?
The
Could you try to show your
presentation.
presentation?
Да что? Иди помоги. Ну что ты? Где?
Демонстрация экрана. Выбрать ее. Где там? Да.
Okay, now we can see.
We suggest graph-based methods for solving some key tasks of the decompilation program. Variably use well-known task for graph methods and solve it. Well-defined static MOS circuit allows to split it into smaller sub-circuits, each of which is a group of channel-connected transistors. Such a circuit component consists of transistors connected with their drain and source terminals, and it provides signal to pass through power and input terminals. Here, an example of grouping transistor circuit into two channel-connected sequences is shown. In graph interpretation, splitting a transistor circuit in sequences transistors is reduced to search of connectivity components in the graph that represents the circuit. The graph for these purposes is transformed by connecting their drain and source terminals and deleting gate terminals. So we have such a graph, and the task of searching for groups of channel-connected transistors is reduced to the search for connectivity components of the graph. There are two such components. Well-defined transistor circuit is a group of two blocks. Pull-down block consisting of NMOS transistors and pull-up block consisting of PMOS transistors. The blocks are dual, represent dual structures, have the same number of transistors in them, and realize mutually inverse functions. Here a group of two channel-connected transistors is shown, and the group of channel-connected transistors on the right is NAND transistors, and on the left is not CMOS transistors, because it has its blocks have different numbers of transistors. Logic function expression that is implemented by pull-down or pull-up networks is formed by tracing passes between power terminals and connection point. Each pass gives a conjunction of the connectivity variables fed to gate terminals. The OR of all conjunctions yields conductivity function in disjunctive normal form. For CMOS gate, the functions implemented by these blocks must be complementary. Otherwise, the structure is not a CMOS gate. To classify CMOS gates, the conductivity functions are represented in a canonical form that is obtained by factoring, algebraic factoring the expressions. However, not all functionally equivalent CMOS gates are topologically identical. That is because of specifics of topological implementation of CMOS gates. For example, the drain and source terminal can be interchanged. Here is an example of such exchanging drain and source terminals, and so the structures are not isomorphic. The topological equivalence of CMOS gate implementations is established by checking whether the corresponding graphs are isomorphic. Here in the table, some experimental results with decompilation problem are shown. Here for each circuit, we can see numbers of N and PMOS transistors, number of found pass gates, and found channel connected components, and then the number of CMOS gates found among channel connected components. Two last columns show the number of classes of functionally equivalent CMOS gates and the number of CMOS gates that are topologically identical. We can see that among functionally identical CMOS gates, practically always there are topologically non-identical. To check isomorphism between graphs presenting transistor subcircuits, they are complemented with edges connected their 4 terminals for each transistor. Then analyzed subcircuit is represented by undirected vertex colored graph, and that graph is sparse. So we can see transistor circuits, their graph, and the graph that is transformed by connecting their terminals. In graph interpretation, the isomorphism testing between graphs consists in comparing their canonical forms, isomorphs. The analyzed graphs are constructed by one by, and each of them, its vertical canonical labeling is generated and hash computed. Canonical labeling is done by the process of building the sequence of partitions for the set of graph vertices. They define an ordering of graph vertices. Graphs with equal hashes are isomorphic, and they are changed in hierarchical space with description of their canonical isomorphs. The proposed methods of computing canonical isomorphs provides fast processing of large and sparse graph. Our graphs are exactly the same, sparse and large. Here is an example where we see the initial partition, vertex partition. It is obtained according to vertex types and degrees. So in the same class, the vertices with the same type and the same degree are included. Here we can see different canonization results for two transistor circuits that they are slightly different. And the difference is the interchanging of their drain and source terminals. Here is the different order. Two kinds of experiments with the developed program were performed. With circuits obtained by CAD systems. In this case, full coverage with logic gates was obtained, and with transistor circuits extracted from layout. Here, the coverage is about 60–70%. In all cases, extracted circuits successfully passed through the verification check. Some experience results are shown in the table. Here we see the complexity of the circuits, then the velocity of the methods. It is estimated in seconds and estimated by the number of transistors processed per second, and the number of logic gates that are recognized in the process of decompilation program. And so the conclusion. We propose graph-based methods for solving the task of decompilation flat transistor circuits in the case when cell library is unknown. And the proposed methods are implemented in C++ as a part of the compilation program. Our future work is to extend the decompilation program with means of recognizing memory and more complex elements. Thank you very much for your attention.
Thank you very much. So while I'm asking for questions of our participants, the next speaker, please try to check the connection and try to yes, please close your screen now. Close the session. Stop sharing the screen.
Так.
You need to stop sharing. Вы должны выключить
I don't
экран.
see no.
It should be a green button which displays that you launching your screen. Please stop this.
Ага, вот. Так, в чем дело? А?
Okay, thank you. So the next speaker, please try to speed up your connection. I'm sure you will be succeed with this. So Sergey Dvoyenko and Denis Pshenichny, metric corrections of similarities based on orthogonal decomposition. Please, the floor is yours.
Okay, dear colleagues, can you hear me?
We see your screen, thank you.
Yes. My screen is here. So, metric correction of similarities based on orthogonal decomposition from tool Russia. Table contents. The idea of decomposition, correction, using proposed to some small real data. So, raw data is a model machine learning. In model machine learning, usually appear as similarities or similarities. And the positive definite similarity matrix represents a limited set of elements immersed in some metric space, usually like Euclidean space. And you usually use the matrix with similarities considered as a scalar products. In the case of a non-positive definite similarity matrix, it needs metric correction to be considered as scalar products. Previous achievements. We have developed novel end-to-end correction technology for optimal recovery of a violated matrix. This approach differs from the well-known multidimensional scaling problem since it doesn't need to recover explicitly the feature space. The technology novelty consists in each metric violation is connected with some member of the set which is supposed to be responsible for the violation in the usual traditional approach, which does not supposed. So what traditional approach? The non-discrete Karnin law of expansion usually used to reduce the dimensionality of the similarity matrix by removing eigenvectors corresponding to negative eigenvalues. As a result, we can calculate a new similarity matrix of the reduced sides to correctly immersed members of the limited set in a reduced space of eigenvectors corresponding only to positive eigenvalues. So the data dispersion is reduced. The novelty of our approach. Empirical functions for paired comparisons are not usually correct mathematical functions of distances or similarities as a scalar products. So according to our novel metric correction here, based on the well-known orthogonal decomposition of a similarity matrix, we propose not to remove but to change negative eigenvalues to become positive ones. As a result, such an optimal correction preserves the dimensionality and of dispersion of raw data. So what does it mean, decomposition? You have a set of n objects represented by normalized matrix S of pairs comparisons with normalized elements as units on the main diagonal and other non-diagonal methods between the unit by module. So the spectral decomposition of this non-degenerated matrix has the form: the A is the matrix of the eigenvector columns. This is an orthogonal matrix. And this is a normalized eigenvectors. So E is a unit matrix, lambda is a diagonal matrix of the eigenvalues. And these eigenvalues are positive and ordered in the descending order. This set of an object is correctly immersed in some metric, usually Euclidean space, of the dimensionality not more than n. This matrix S consists of normalized scalar products of objects. The raw data matrix X and the feature space with dimensionality M with dimensionality not more than M are not presented here. We suppose this space has been lost. Otherwise, we can directly calculate scalar products of objects. Based on the decomposition of S, of the non-degenerated, this matrix is not degenerated, the diagonal matrix lambda is decomposed as shown. So you can see trace of this lambda matrix is a trace of matrix S and is a dimensionality of the space. What does it mean, correction of metric violation? In data analysis, the decomposition in terms of orthogonal vectors usually used for the correlation matrix of features, targeted to reduce the dimensionality of the space of eigenvectors of the correlation matrix R to the new value less than initial in different tasks. In particular, the non-correct matrix R has negative eigenvalues, hence the projection of raw data matrix X in the new orthogonal subspace is usually used. It is important to note such the projection requires the raw data matrix X itself to get new one, X prime. In this case, the dispersion for raw data, the total dispersion, is reduced to the new size, M prime. Unlike the classical approach, the spectral decomposition in our investigation induced to the set members represented only by scalar products. Scalar products in the non-positive quadrant of the metric space used as the similarities. It doesn't not matter for us what they are, features or objects themselves. In the case of metric violations, in the set configuration, in a hypothetical space, we have noted the spectral decomposition of the matrix S has negative eigenvalues. So we propose here not to reduce raw data, but replace negative eigenvalues in the decomposition by the appropriate positive values to get as a result new matrix lambda under the cap of the same dimensionality. Finally, the matrix S under the wave is recovered in the form of such decomposition. Nevertheless, the new matrix S under the wave appears to be non-normalized, so we need to normalize it to get the diagonal elements as units. After that, the trace of this matrix will be not more than n. So normalization is represented here. So after that, we can decompose the S under the hat again. And after this, we can see that the trace of the new matrix S under the hat is n. Consequences and opportunities of this new problem. Zero similarity matrix can have other type of violations. For example, with non-diagonal elements exceed diagonals 1 by the model. It is possible in general to formulate any suitable problems to find the corresponding set of eigenvalues for similarity matrices. For example, to provide a suitable conditionality. What does it mean using the proposed approach for real data? Example, the psychologist Nebelitsyn obtained data during his investigation of light sound sensations imposed by rhythms in the form of correlation matrix. It represents statistical interconnections between power biorhythms of 11 frequencies of brain, like alpha, beta, and theta rhythms in electroencephalograms. So this is the example of this correlation matrix. This matrix contains 10 positive and 1 negative eigenvalue. So it has metric violations. We have already studied this matrix in order to correct it and determine the optimal conditionality based on the end-to-end metric correction technology from the previous investigation, as a result of the previous investigations. So here is the example of the corrected matrix. We try to replace the negative eigenvalues from the negative to some small positive to get minimal corrections of the initial matrix. So the conditionality of the matrix 2 bad, you can see, is 122,000. So, early, a statistically inspired condition of this matrix give us the conditionality is about 60. And now we replace a negative eigenvalue with a positive value. 0.612. And after normalization, we can get the correct matrix with positive eigenvalues, and with the last eigenvalue is 0.06. So the final conditionality is practically optimal. As you can see, these matrices are practically the same. Initial, recovered, and recovered optimally. So the optimality of all corrections are based on the cardinal law properties of the orthogonal decomposition. So what does it mean as conclusion? Optimality of the correction is supported by the properties of the cardinal law of expansion and the correct selecting of the new value of the corresponding eigenvalue. Here we face the well-known perturbation theory of eigenvalue problems. This is the one of the first publications of Relish. In the framework of this general theory, the novelty of our approach consists in the attempt to make a perturbation in eigenvalues first, to recover then the similarity matrices second, used in machine learning. That's all. Thank you for attention.
Thank you, Sergey. Thank you for your very intensive presentation, and I hope you will start chatting with those who will ask you questions using our chat in Zoom. So now I need to proceed with the fourth presentation, which will be made by one of the co-authors, Viktor Krasnoproshin, Vadim Rodchenko, and Anna Karkanitsa. Pattern recognition based on class distinctive features. Please, you have a floor. Please share the screen and start the presentation. Thank you. Now we see your screen. Thank you.
Okay. Good afternoon, dear colleagues. It is my pleasure to participate in the conference. And let me present the research that was done together with my colleagues, Viktor Krasnoproshin and Vadim Rodchenko. So, pattern recognition based on classes' distinctive features. So if we return to primary sources and recall the definition of data mining coined by Gregory Petetsky-Shapira, it says that the main goal of data mining is to identify in data a previously unknown, non-trivial, and potentially useful and interpretable knowledge. And this knowledge can be used for decision making. So now let's have a look at the simplified scheme of machine learning process and data mining process. So in machine learning, we take as an input the training set and the testing set. And the learning process is focused on building an algorithm on the base of the training set. And this algorithm is usually the classification algorithm that can be used to classify the testing sample. So the main output of the learning process here is algorithm. In data mining, we have a bit different approach, how the learning process is implemented. So we take a training set as an input, and we are expecting to get a knowledge. And this knowledge will be used to construct the classifying algorithm that allows us to classify objects. So the practical usage of the explained scenario revealed to a number of shortcomings, or let's say disadvantages. Firstly, with machine learning, when we are preparing the training set, it is actually a time-consuming process. In some cases, it takes 80% of overall effort and usually involves experts. Secondly, selecting a family, or let's say the model of algorithms, it is a non-trivial task. Usually data scientists do it. So again, the process involves some experts. And that's why we can conclude that learning can be implemented only in automated mode, not automatic mode. The resulting algorithm that we will get looks like a black box. So the algorithm that can be hardly interpreted. And even if these algorithms approximate the unknown dependency, we don't have too much knowledge about this algorithm. That's why we call it black box. And finally, even if an algorithm is found, it is based on the training set. So it means we still don't have information. Are there any other feature subspaces where the problem is solved more efficiently? So the main output of this explanation is to explain that our algorithm that we get as a result of the learning process, actually algorithm that we can trust, but that can be hardly interpreted. So to overcome the mentioned disadvantages, we propose the alternative approach. And this approach is based on the hypothesis of compactness. So in the object space, classes form compactly localized subsets. So again, if we go back to traditional approach in the learning process, it is reduced to the construction of decision rules. The decision rules are based on a priori specified, or they are priori specified, even up to parameters. So the learning process involves searching of these parameter values. The alternative approach is based on the idea that we are searching such combinations of features that are most informative to distinguish classes. And this combination of features will be taken also from the priori dictionary of features. Identification of the features occurs as a result of constructing a feature spaces where class patterns do not intersect. So to show the alternative approach, we can have a look at this geometrical representation. In the traditional approach, we are building a function, let's say function that is shown here as a line, and it depends on some number of parameters, and it looks like it splits the overall set into regions. In the alternative approach, we are trying to build feature subspaces that allows us to classify objects. So if, for example, there are two features, X and Y, we are expecting that these features will uniquely identify objects from the training set. And now a few words about the statement of the recognition problem. Based on the proposed idea, we would like to present the, another problem statement of the recognition problem. So in contrast with the traditional approach, it is required to construct an algorithm that would approximate the target dependency on the entire set of object X. In the alternative approach, it is required to find a feature subspaces where class patterns do not intersect. And based on these patterns, the next step is to construct an algorithm that would approximate the target dependency on the entire set. And this second step will be very simplified, because if the feature subspaces is known, so the process of constructing the algorithm becomes trivial. So to implement this idea, the supervised learning algorithm was designed. So let's say that we have a training set, and this set is formed on the basis of so-called a priori dictionary of features F. Let's also V be a set of all possible combinations of features from F. So we are going to build class patterns in the form of cluster structures based on the training set. And the priori dictionary of features will be used. So in this slide, there are steps of the design algorithm, and the algorithm is aimed to construct a set of features where class patterns do not intersect. So let me skip these steps, because the general idea of the algorithm is explained, and in details algorithm is described in the published paper. Okay, so now it is important to analyze what is the outputs of the algorithm. So after the algorithm execution, the set of feature subspaces will be constructed. Each combination of features from the set defines a decision space in which class patterns do not intersect. So based on this combination, we formulate the previously hidden and empirically revealed pattern. In the feature space of subset VI, class patterns do not intersect. So we are getting a knowledge about feature subspaces that allows us to classify objects. Within a specific applied problem, the revealed combination of features can be interpreted by the domain expert. And this is the important issue, because in contrast with the black box that we have in the machine learning process, this approach allows us to have knowledge, so kind of white box that can be interpreted by the expert. To show and prove the efficiency of the approach, let's have a look at the results of the numerical experiment. To explain it in simple way, we are taking a simple data set where we have 20,000 7-bit integers, including 10,000 multiplies and 10,000 not multiplies by 5. So from mathematics, we all know that number multiplies by 5 if it ends with 0 digit or digit 5. So applying the design algorithm for the given data set, we will analyze possible combinations of features from the set V. So like units, tens, hundreds, thousands, tens of thousands, and so on. So the table that is shown on the slide demonstrates that we got the M5 set and an M5 set. So numbers multiplies of 5 and numbers not multiplies by 5. And the conclusion from these results is that M5 have no digits 1, 2, 3, and so on 9 at the unit place. And the set N M5 have no digits 0, 5 at the units place. So it is also clear that 0 here and 0 here says that our class patterns do not intersect. If the same experiment will be done for feature hundreds and thousands, or tens of hundreds and hundreds of thousands and even millions, we see the intersection of classes. So, and it simply proves that we have actually only one feature, units, that allows us to classify objects. So analyzing all of the features and possible combinations of features, we got intersection equals to 0 only for the feature units. So the feature units provides an absolute separation of classes of numbers that multiplies of 5 and not multiplies of 5, since we got interaction that is 0. And it is also important to note that the algorithm running time is 0.35 seconds. That is faster than comparing with the same approach that was described for the learning process in machine learning. So these experiments allows us to conclude that alternative approach based on searching the feature subspaces can be efficiently used to pattern recognition and object classification. So as a conclusion of our research, we can say that as a result of the research, an alternative statement of recognition problem is proposed. An alternative approach to learning process is also proposed, and this approach ensures class separation. For that approach, the supervised learning algorithm is designed, and it is aiming to find informative combinations of features that helps us to classify objects. And this algorithm allows also to detect previously unknown dependency. And this dependency can be interpreted in terms of the subject domain. The effectiveness of the approach is confirmed by the results of the numerical experimental model data. That's all. Thank you for your attention.
Thank you very much for your approach to the pattern recognition problems. So if we have no questions, so I'm just asking to those who are in our Zoom session. So now I'm passing the focus to the next presentation, new algorithm for building effective model from prediction models and using parallel data, which will be presented one of the co-authors, Zurab Grezatshvili, Merab Phovilishvili, I'm sorry for my pronunciation, and Natella Chvadze. Please, you have a floor now. So you muted, yeah, now we have a focus on you, but please unmute your microphone. Yes, now we see you.
Sorry, do you hear me?
Yeah, we hear you, but quite a big echo.
Hello?
Hello.
Yes, okay. I would like to share the screen.
You need to turn off your sound from the second computer.
Yes,
yeah,
exactly.
I turned it off. I turned it off.
Yeah, that's nice.
Okay,
perfect.
Is okay.
Now please
so now,
show us your screen.
Yeah? Just a moment. One second, sorry.
That's okay, yes.
We are trying to share presentation on the screen. But I will start anyway, and okay. Building much more effective new hybrid models for prediction models using parallel data is discussed. the algorithm for selection of model pairs and its advantage over any best prediction model is provided. Some prediction models are based on using of parallel data, although it must be noted that the term parallel data is definitely explained in each of them. In practice, parallel data is used during prediction of various... do you see the presentation, sorry? Hello?
No, we do not see your presentation. We just see your camera.
Okay.
We see you, but we do not see your presentation.
Okay, I continue. Sorry. We are trying to share it, but cannot share.
Sorry to show your screen.
If I go out and turn again, maybe it will help.
Okay, please try.
Okay, 1 second, sorry.
Yeah, while our colleagues is trying to connect to share the screen, I would like to say that we divided our conference into 2 sessions. The first session, A, means the problems about pattern recognition. So these theoretical problems according to the papers you presented to us. The second session is about more applied things, image analysis and so on. So it's also pattern recognition, but more practical one. So each day we will have 2 or 3 sessions which devoted to pattern recognition and image processing, applied problems, or vice versa. So this is how our conference is divided into 2. After the lunch break, we call it big break, we will have a session about the practical problems. So I think I will also be a chairman of this conference. So now, finally, we see your screen. Please proceed with the presentation. Thank you.
Sorry for the delay. Yes, sorry for the delay. We start. New algorithm for building effective model for prediction model using parallel data. So, building much more effective new hybrid models from prediction models using parallel data is discussed. The algorithm for selection of model pairs is advantage over any best prediction model is provided. Some prediction models are based on using of parallel data, although it must be noted that the term parallel data is definitely explained in each of them. In practice, parallel data is used during prediction of various events, including natural disasters, earthquake, landslide, tsunami, mud flow, and etc. For prediction economical, political events, for effective solving of prediction tasks in the sphere of medicine and other fields. The definition of parallel data is based on introduction of new type of dependence between the data, which is called parallelism between the data. The definition of parallel data is based on introduction of new type of dependence between the data, which is called parallelism between the data. Parallelism between the data is mutual dependence between those data which are used for prediction of the same event. Various data may exist in different periods, parallel by time or location, parallel by location. Now, success probability of this prediction. On this slide, we describe the main idea of algorithms for building of prediction models is reviewed by us through parallel data. Let us assume that there are several models of prediction. From them, it is necessary to select such pairs, triples, for several models, which give much better results than a single best model from them or two models separately. This algorithm was the following. Such models were found for which the number of coincidences of unsuccessful predictions for some given event was as low as possible, but successful predictions were necessary for them. In this article, we will establish 5 lemmas for the task of static prediction and show how the accuracy of such models is increased through our algorithm. Specific data are taken from earthquake prediction task. Each prediction model is built based on certain predecessors. For earthquake, the predecessor is geophysical phenomena mainly, which precedes the actual earthquake. Assume that we have several prediction models which provide some predictions through their predecessors. For example, for earthquakes, when it would occur and which location and with which magnitude. We study history. Let's assume that there is plenty of data and it is necessary to calculate based on predecessors how many times the prediction of earthquake occurrence was given and how many times actual earthquake occurred. Assume that we consider the necessary predecessors and the models created for them, A1, A2, and AN, okay? We calculated the number of earthquakes predicted by each predecessor, P1, P2, Pn. For each Pi, let's calculate quotients of M, the number of actually occurred earthquakes, write it in percentage and designate with Ki equals M/Pi 100%. Put the sequence of model success in descending order, and this sequence denotes as K1, K2, Kn. Lemma 1, if such pairs of models are selected for which the number of coincidences of unsuccessful predictions for some given event was as low as possible, but successful predictions were necessary for them, then the success probability calculated for combination of any pair so selected is always higher than or equal to the success probability of best from them. If we take best Ki and pair it with any, even the worst value Kg, then their combined result is not worse than Ki. If we take the best Ki and pair it with any, even the worst value Kg, then their combined result, as I already mentioned, is not worse than Ki. Proof is based on the fact that for the pair Ki and Kg, where Ki is less than Kg, then the intersection of their successes, of course, is less than or equal to Ki. Lemma 2. The higher number of intersections of prediction models, the better prediction we would get. For example, the best triplet combination of 3 predictions would give better results than the best pair of predictions. The best quad gives better results than the best triplet, and so on. Now, if we talk about lemma 4, modification of prediction model, it means recalculation should be done from the day of the last earthquake occurrence. In accordance with Lemma 2, the prediction pairs are selected. When selecting them, we determine the number of accurate coincidences of predictions. Lemma 5, when selecting the pairs of prediction models, an approximate coincidence should be taken into account. And now, the conclusion. We considered the possibility to build much more effective new hybrid models from prediction models using parallel data, and by means of lemmas, we state that the advantage of selection of model pairs over any best model of prediction, it was shown that the more is the number of model pairs, the more is advantage of the lesser number of pairs. The best pair is the one that does not have intersection between each except actual occurred prediction. When to reselect the pairs of prediction models, and that is necessary to consider approximate coincidences of predictions in this case. This is the literature which lists articles by authors on the topic, and finally, sorry for technical problems, and thank you for your attention.
Many thanks. I should say that finally it was okay, so your presentation was good. And I hope that all of us will have a chance, actually we'll have a chance to chat. I remind you that there is a worldwide YouTube stream now, so we have an audience on YouTube, we have participants on Zoom, so please start chatting, ask questions.
Alexei, I would
yes,
like
exactly.
to ask a question.
Yes, of course. Yes.
Alexei, I would like to ask a question.
Yes, of course, you have a floor now. Please ask the question.
Yeah, okay. Thank you very much for your presentation. I would like to ask you whether you have any examples where you applied your predictive model for solving some application problems, or just a theoretical one.
For application of this model, a lot of data are required, big volume of data. While earthquake, this data which we possess are few. We don't have a big range of data. We were able to do it for the prognosis of valued course, and we did it. And we saw that our model identified the pairs which gave us an advanced result, better results. If we will have more, possibility, more data for application of this model in different other directions, we will be able, while the earthquake, for example, to raise the 3% of probability to the 70%.
Okay, thank you very much for your response. Okay, thank you.
Okay, any other questions? Yes, as far as I know, actually, Central Asia region is quite good in such kind of work, so connected to climate change and seismic tasks. So that was one of the examples. I would like to give a floor to the next presentation with the work entitled as Search for Genomic Mutations Associated with Drug-Resistant Tuberculosis. So please, you have the presenter, you have a floor now. Present yourself. Now we have, yes, we see your screen.
Oh, nice. The topic of my presentation is search for genomic mutations associated with drug-resistant tuberculosis. So today we'll talk about the purpose of this research, which data we use and how we prepare it, which single marker and multi-marker tests we used, and which results we obtained. The purpose of this research was to analyze genomic and phenotypic data and identify mutations and features related to drug resistance to the first and second line anti-tuberculosis drug. We consider it isoniazid, rifampicin, ethambutol, and streptomycin as first-line drugs, and fluoroquinolones and aminoglycosides as second-line drugs. Tuberculosis is still actual nowadays. Every year, near 10 million people fall ill with it, and about 1.5 million died from it each year. It is top 10 infectional killer. Usually it takes much time to treat it, at least 6 months, and if the first treatment failed, the recurrent case likely will be drug resistant. Drug resistance is an ability of disease-causing germs, in such cases as tuberculosis, to continue multiplying despite the presence of drugs that usually kill them. In this research, we use data collected from the drug-resistant tuberculosis project. It contains more than 1,000 tuberculosis cases with results of biological tests for drug resistance and genome sequences. At first, we removed duplicates and cases with conflicting results for drug resistance. For example, if one test system showed resistance and another insensitivity, we exclude such case. Also, we applied a minor allele frequency filter. So we took only mutations that occurs more than in 1% of samples. With help of phylogenetic trees, we identified two populational subgroups in the original data. With help of Pairwise correlation table, we found cross-resistance between first-line drugs, fluoroquinolones, and aminoglycosides, but no cross-resistance between first-line drugs and second-line drugs. Single marker tests check association between observed drug resistance and individual mutations. They are modifications of classical statistical tests. We used feature exact test and Cochrane-Mantel-Hansel test. They're both based on such contingency tables. To visualize test results, we used Manhattan plots. The higher the point along ordinate axis, the more its significance. So, for example, for isoniazid, Cochrane-Mantel-Hansel test identified two mutations with a relatively low p-value. Single marker tests revealed sets of mutations associated with drug resistance to individual first-line drugs, their combinations, and groups of second-line drugs. However, they were not able to identify mutations associated with resistance to individual second-line drugs. To verify obtained results, we used the BDREAM database that includes already known mutations. The key difference of multi-marker tests from single marker is that they consider additive effects between mutations. So they consider mutation 1, 2, or 3 not as individual, but their different combinations. As multi-marker tests, we used algorithm for searching for combination of mutations with boosting and factor analysis of mixed data with linear mixed model. We took genomic data and phenotypic features. With help of factor analysis, we obtained a set of uncorrelated features, and then we built a linear mixed model. This model considered fixed and random effects. Fixed effects is a base regression in the data, and random effects are effects inside each subgroup. Each subgroup may have its own unique features like specific treatment regimen in the country or healthcare system itself. So it is features that are not associated with drug resistance. To obtain model, we use cross-validation. We used 4 basic metrics: precision, recall score, and accuracy. For the first-line drugs, scores are good. For fluoroquinolones, scores are satisfactory. And for aminoglycosides, scores are low. That means that we can build a good classifier for them. We went deep in details of this algorithm, only discuss the main idea. So we want to find different combinations of mutations and test how they're associated with resistance. So we need to enumerate them somehow, but the number of mutations is huge, and it is hard to enumerate all of them. So we want to switch from enumerating mutations to enumerating samples, because number of samples are much lower. We applied such algorithm for second-line drugs and obtained a list of mutations with informative score calculated by the formula. Despite some values are higher than another, we still can't build a classifier for them because accuracy is too low. So the correct way to interpret the results is that this list of mutations occurs more frequently in the samples that are resistant to fluoroquinolones that in those that are sensitive. So we consider a single marker and multi-marker tests that can be used to test mutations associated with resistance. This test works good with individual first-line drugs and their combinations. However, they found mutations that includes individual mutations associated with drug resistance to their second-line drugs, but they alone are not enough to build a good classifier. So that's it. Thank you for your attention.
Thank you for your very productive and pressed presentation. So if we have questions, please, you may ask now. You have a chance. So we have no questions. No. Well, actually, so YouTube stream now is has a little bit in lag. So probably let's say 20 seconds. But still, so I'm not supposing that we have questions, because we have just one question, just an organizational question in the YouTube chat. If we have no questions in our Zoom, so I would like to thank you, all of you, in this session. And so now I'm announcing our break. We call it big break till 2:30. So when we will start our session called B1 about practical problems of pattern recognition and information processing. So see you 2:30. Thank you. Ladies and gentlemen, good afternoon. I'm happy to invite you to our afternoon session, which will be dedicated to practical problems with pattern recognition and image analysis and information processing. So I'm also very happy to introduce you our guest in our studio, Professor Alexander Nedves, who is a Dean of Faculty of Applied Mathematics and Informatics in Belarusian State University. So, and now we have a session called B1, and the chairman of the session is Professor Vladimir Golovko. So I'd like to ask Vladimir, is he ready to conduct the session or not? So please. So, yeah. Please, I see actually, so half of your face now. Could you tell us, will you manage the session? Or should I do this instead of you? Okay. Well, let's, yeah.
Do you see me? Okay.
Unfortunately, your mic is too low. Could you do something with the mic, or while you settle the microphone, so I will continue this session. Probably we will exchange it later, okay? Because your mic is very low, the volume. Okay, well, I will continue because actually, so there are some technical problems with our chairman and the end of the computers. So the first presentation of our session will be introduced by Svetlana Ignatyeva, Richard Bogush, and Sergey Blameyko, entitled Joint Dataset for CNN-Based Person Re-Identification. Please, you have a floor, share the screen and start the presentation. Thank you.
Hello.
Now we see your screen, so you can start.
Hello, my name is Svetlana Ignatyeva, and I'm present joint dataset for CNN-based person identification, prepared by Svetlana Ignatyeva and Richard Bogush from Polsk State University and Sergey Blameyko from Belarusian State University. Person identification is a process of identifying a person in another place or at a different time using video surveillance systems. Video sequence from several CCTV cameras are divided into frames. On each frame, persons are detection and bounding boxes are formed. Features are extracted from the array image compared with the features of images from the gallery, and as the system output, we have the identification result. Person identification has a wide range of applications and can be used to solve a large number of tasks. For example, tracking people using CCTV cameras, finding a person in a large gallery, analyzing visitors in a store, checkpoint of secure enterprises, and more. The identification comes with a number of problems. The main problems are the following. Camera angle of view. Depending on the position in relation to the camera, the object will look completely different. Pose variability. A person can take on a very large number of positions in space. Lighting. The co-perception is highly dependent on the lighting debris at different daytimes under different weather conditions in the typical lighting presence. Resolution. Different CCTV camera may differ in the result frames quality. Background clutters. Pre-identification test is often a complaint be a complex background presence. Occlusion. The people in the wider are moving and can often be obscured by other people or landscape elements. Appearance. People can be dressed the same or very similar for different reasons. People can change their appearance when they move. And domain shift. This problem is due to the fact that wider cameras can have similar resolutions, smoothing at different times, different degrees of illuminations, different camera position give different backgrounds. This is of great importance when working with datasets because each of them is a separate domains. In our work, we considered several datasets for identification. Market 1501 was assembled at Tsinghua University in supermarket front and includes more than 32,000 handcrafted bundle boxes. CubeMT-MC ReID is a subset of the CubeMT-MC datasets executed in March 2014 from the campus Duke University. The images were taken from 8 CCTV cameras located between the buildings and include more than 36,000 bundle boxes. LPV is obtained from 3 different stands. The first stand includes images from 3 cameras and other 2 stands include 4 cameras. The full dataset contains 2,731 people and 592,438 bundle boxes. CUHK02 contains 186 people and 5 camera view space. The dataset was collected from the Chinese University of Hong Kong campus. The dataset contains sensitive data, and the authors asked that the privacy of CUHK students be respected. CUHK03 was obtained from the Sun campus of the Chinese University of Hong Kong too, and contains 1,467 people. And we developed our own dataset called PRIP'2021 for its formation by the sequence result from volunteers are used. For each person, there are from 1 to 7 value sequence with different location, illumination levels, image quality, and distance from the camera. To extract bundle boxes from frames, they will be for detection algorithm. The collected bundle boxes were removed manually. In total, the dataset contains images for 54 people and includes 5,609 bundle boxes. For the ID is split into training and testing data. For training, 30 people are used. For testing, 24 people used. Joint dataset is challenging. This is due to the fact that different datasets have a different way of writing names or different by location in Lighthouse hierarchy. Certain names can contain useful information such as camera number from which the image was taken and SAN number. In additional identifiers and sequence camera number, rows can be the same in different datasets, but they will belong to different people. All this was taken into account when creating a large joint dataset. For correct identification algorithm operations, the image file names were brought to a single recording format. In total, trained sample of large joint dataset includes 8,690 identifiers. As a re-identification algorithm, the personal ID baseline approach algorithm was used, which was trained for 60 epochs, which a trained batch size of 32, a learning rate of 0.05, and the learning rate with a factor of 0.1 times after 40 epochs. This algorithm assumes that the trained neural network extract features for each person located in the test sample gallery. Then for each player, there are images whichever is learned. The cosine distance is used as the similarity matrix. The image obtained from the same camera is the replaced image excluded from the function feature table. The training time for each experiment varied from 1.5 hours to several days and depended on the trained sample size, backbone network, and computer parameters on which the model was trained. On the training graph, you can see a sharp drop in the value of the loss function. This can be explained to be the change in the learning rate after the 14 epoch. Our experiment can be divided into 3 parts. The first set of experiments consisted in the fact that training was carried out on one dataset and testing on another. You can see the result of this experiment in the table. The BSUIR has examples when training and testing were carried out of the same datasets. That is, train and test sample belong to the same domain. But this result is not objective for invisible domains. The best rank 1 and mean average precision value corresponds to the experiment when testing invisible datasets if the trained sample was an LPV dataset and testing was carried out on market. When tested in invisible datasets, the LPV dataset generally showed better training ability compared to market and Europe, which is most likely due to the significantly larger size of the LPV trained set. If you pay attention to the example when LPV acted as a test sample, we can see that the re-identification accuracy is higher when trained on the market than on the Europe, which gives us reason to assume that the different identifiers number is more important than the number of bounding boxes. The second our experiment part was to gradually increase the trained sample. Where we can see then an increase in the dataset for training the CNN leads to the increase in the re-identification accuracy. It was found that the best test result for re-identification can be obtained when the trained sample includes data belonging to the sound domain as the target one. The best accuracy was achieved when combining all 4 datasets for training. During the third part of the experiment, the approach was slightly changed when creating a trained sample. The data from the market CUHP02 and CUHP03 sets were not divided into test and trained sets, and they did not allow testing on market and Cube. Testing on the LPV dataset showed an increase in the rank 1 accuracy to almost 51 in the case when the LPV is an invisible dataset, which is almost 1.5 times higher than when given one close dataset for training. Adding LPV to the trained sample allowed us to obtain the maximum values for all estimate metrics. The maximum rank 1 accuracy achieved for the full rate dataset is 68.293. The reason for this may be test sample size and composition. Some of the PRIP dataset images were obtained from only one camera, and the re-identification algorithm used cannot detect them. With a future dataset expansion, this will be taken into account. In conclusion, we can say that when using convolutional neural networks, the trained sample is often great importance. dataset verity and thus all the re-identification system to have better generalizability and reliability. Using a larger dataset allowed us to improve rank 1 and all mean average precision on all test sets. In future research, we plan to expand the POVID database we have collected. Thank you for your attention.
Thank you for your presentation. Please, colleague, ask questions. You may ask here in Zoom chat, Zoom orally, or in the YouTube session. Yeah.
Okay. I'm Alexander Nedved. I'm ask Svetlana about data sets. Everyone knows that data sets very important for training model, and my question is there any dependencies your data set from weather, and have you any sets, maybe any table when present description dependency weather from your data set? Thank you.
So actually, there are different models, data sets you provided in the presentation. That data sets must include different samples with different conditions, at least air conditions, so light conditions. Have you any statistics? What kind of, how many samples with these and these conditions are there in data set you provided in the presentation? At least light, for example, lighting. So face with different lightings.
I don't understand questions.
Okay, I think my colleague will repeat in Russian currently for you.
Светлана, вопрос в том, что есть ли какой-то набор классов в ваших датасетах, которые зависят, допустим, от погоды или от освещения, но именно сколько процентов там дождь, сколько там солнце и так далее?
Ну, мы такую статистику не собирали, то есть, ну, как бы есть примеры изображений, которые получены при солнечных условиях, есть при пасмурных, есть при хорошем освещении, при плохом, ну, вот, в процентном соотношении не проверяли, ну, не считали.
Okay, one more question. Just in Russian or English, what do you prefer? I will tell it in English and then repeat in Russian if it will be a problem. Have you ever participated in any worldwide competitions, challenges with your models or not? Участвовали ли вы в каких-то соревнованиях международных, хакатонах или вот в данной, с данными моделями?
Нет, не участвовала.
Спасибо. So, if we have no questions, I guess we have no. We will go further to the next presentation. I hope will be made by our Italian colleagues, entitled Back of Deep Features for Classification of Gigapixels Histological Images. So please, colleagues, try to connect. I would like to ask previous presenter to switch on screen, stop sharing the screen, because we need to proceed with screening from the other participant.
Okay.
Yeah, while lady trying to stop the screen, you can just introduce yourself.
Yeah, well, I come from the University of Naples, and this work is a joint work between the University of Naples and the National Italian Research Center. The authors are Nadia Brancati, Maria Crucci, Crispino Cicala, and I. And I'm Daniel Riccio, and I will present the that is on the classification of histopathological image, that is trying to work with images to classify tissue with respect to normal tissue and cancerous tissue. So I will share my screen.
Yes, thank you. Now you can share your screen.
I will show the presentation. Can you see the presentation?
Yeah, the census of the year 2020. Can you share the screen? Exactly, we see your screen.
Okay, perfect. So I can start. Well, breast cancer is the main reason death of the over of the world. So the interest in trying to classify different kind of tissue, different kind of tumors, is quite important, and the attention of researchers on this topic is ever and ever increasing. Well, the main science studying this kind of problem is the histopathology. And pathologists in general examine the images at microscope and try to take a look to the whole image just to study the configuration of the cell in the tissue. And then they focus the attention on specific part of the image because they are interested in recognizing some specific pattern into the tissue. And the problem with this kind of images is that the resolution is very, very high. I will slide the image, that is an image like the part of one you can see in the slide, may reach billions of pixels. So when we try to apply some new techniques based on convolutional neural networks, for example, the real problem is how to fit these images to the current model of CNN, because they can just work on images with a limited size. In many other fields, the innate solution of resizing the image can work, but in this case, it is not possible because histopathological images have a very high resolution, but they include rich information at level detail. So just resizing the image, we lose this information and jeopardize the results in terms of classification. The other idea is to partition the image into small patches and then work on single patches independently by applying maybe CNN models. But in this case, the problem is that, as I said before, also the pathologists just take a look to whole image and then try to focus on specific details into the image. So also the relation between different parts of the tissue into the image are very, very important for classification. And if we work just on some small pieces of the image, we are not able to extract all the information we need to classify the final image. For the reason, we present a different kind of approach that merge together three different concepts from the state of the art. The first one is the bag of words. That's a method that is used for a long time for image classification. The other one is the representation learning, how we can best represent the information into an image. And the last one is the co-occurrence matrices. How many times a pattern occur into an image and how to use this information to classify the image. So our approach partition the image, the input image in different patches, extract feature from these patches, but use this feature to construct a unique tensor that represents all the image and is some kind of compressed representation of the whole image. And then we try to use deep networks to apply classification to this kind of tensor. So let me take a look to some specific steps of the work. We have a manually annotated data set in which we know exactly which are the patches that represent normal tissue and which one that represent tumoral tissue. So we can well separate normal patches from cancerous patches. So we used this annotated data set to perform a fine-tuning of a residual network, that is the ResNet 18. And we fine-tuned the network just to solve the problem, the binary problem of separating normal patches from cancerous patches. But in this case, in this step, we are just working at patch level. This is very important because we can exploit this deep network just to extract features from different patches. And we extract representative features with respect to the normal and cancerous patches. So we use the network to extract the feature from the patch, and then this feature, that is a feature vector, can be considered as a simply as a visual word. So we can apply to this feature vector the original concept of a bag of visual words, and then we can apply k-mean algorithm, where k is the number of cluster we want, and also represent the number of bag of deep feature words we want. So we fix k, and then we can apply the k-means algorithm. We do that on our dataset, and we can see that the ResNet is able to separate the normal patches from cancerous one, and you can see in the figure which is the separation between blue dots and green dots. If we take a look to the distribution of the patches into the clusters, we can see that generally in a cluster, we can find normal patches or cancerous patches. So we can say that the bag of deep feature words we constructed is quite representative for this problem. So we start from the wall slide image. We partition the image in patches, and then we apply the ResNet 18 to each patch, and then we extract the feature from the patch. We use this feature vector to assign the patch to a cluster. So we can replace each patch into the original image with the corresponding cluster number. And then we can transform the original image in a cluster matrix. Since we fixed the number of clusters to 256, we can also talk to the clusters like a gray level pixel. So we can also represent the image, the cluster matrix like an image. And what you see in the bottom of the slide is what the whole slide image look like when we transform it to a cluster matrix. But cluster matrix is quite important because it's the starting point for searching for patterns into the image. So if, for example, if we consider two different patches into the original image, we assign each of the two patches to the corresponding cluster. For example, the first one to the cluster K, and the second patch to the cluster K prime. So we can just check if this cluster occurs at a distance that is less than a given threshold D. So we check just for a couple of patches that fall at a small distance because we are interested in considering the neighborhood of a given patch, just to take into account for the topological relationship between patches. So for each couple of patch, we can assign the corresponding cluster, for example, K and K prime. And we also take into account for the distance. They are at a distance D, the one from each other. Then we can consider these three information like a pattern. And then we can search into the cluster matrix for all the occurrences of this pattern. And then we can accumulate this kind of information. If we consider the first cluster, the one with the lower number as the first index, and the one with the higher number as the second index, and the distance D, then we can put this information in the upper part of a three-dimensional matrix that we call tensor. And then each one, the pattern SP appear into the image, we can increase the corresponding position. So we are just counting the number of times that this pattern occur into the cluster matrix. But we can also store a different kind of information because each patch is characterized by a feature vector. So we can also consider the relationship between these two patches. And we can just compute the correlation, the Spearman correlation between the feature vector representing these two patches. And we can accumulate this information in the lower part of the tensor. Since the upper part is just counting, so the value of this part range from 0 to infinity. While since the second part is come from correlation, the value range between -1 and 1. So we have to normalize the range, this range of value, and we can map both the parts to the range 0, 1. And then, since we have just the same range of value, we can merge together the upper part and the lower part in order to obtain a single tensor. And then we use this tensor, that is a new compact representation of the whole slide image, to feed a new deep network, just classification. And then we train this new network to solve a binary classification problem. That is the image normal or is the image cancerous? I see that I have a network problem. Can you hear me?
Yes, we can hear you.
Okay, so I go on. Excuse me. We tested our approach on the dataset Chameleon with 400 images that are split in the normal tissue and tumoral tissue. We used the 270 image for training in the dataset, so just to be comparable with other results in literature. As I said before, we fixed the number of clusters to 256 because we observed that the number to provide the best results. The dimension of the patch is the one required by the residual network we used, and the length of the feature vector we used to characterize the patch is just 512 real number. We measured the performance with respect to standard metrics like accuracy, measure, specificity, and so on. And then we performed the different experiments just to analyze which part of the tensor was most informative with respect to different performance measures. And we can see that when we use the whole tensor, so both information coming from counting and correlation, the best performance is obtained for the accuracy and specificity. While if we are interested to the F-score, that is the highest capability of the method to separate between normal and cancerous, then the best performance is provided by the distance, that is the upper part of the tensor. But in general, if we want to try to maximize all the measure, so to obtain a high value for a whole measure, that the most informative part of the tensor is the lower one. That is the one that also consider for correlation, because the lower part taking into account both for where the patch are placed and which is the correlation between the two patches. So we can say that the best performance is provided by the correlation when the distance between two patches is lower than 8. If we consider higher distance, maybe the patches are too far each other, and then they do not provide any informative data for classification. So in conclusion, we try to cope with the classification of histopathological images, which are very huge and difficult to treat by means of actual deep neural network. And we try to solve this problem by changing the presentation of a full slide image by constructing a tensor that is a more compact representation, still preserving most of the informative content of the original image. And the results we obtained, we know how outperform the one provided by other methods in literature, which try to solve the same kind of problem. Now we are still working, trying to reduce the size of the tensor, or try to increase the accuracy of the whole system. So thank you.
Thank you very much for your very straight and productive presentation. So colleagues, you may ask now questions. I will just keep my silence for a while.
Okay, I got one. And Daniel, thank you first of all for your nice presentation. I just want to inform you that we are dealing with this problem for a long time already, and we participated in Chameleon, and we are on the paper, which is published, you know, after this competition. Anyway, so I'm a little bit confused about that, the last table. Is this the accuracy so low, or this is something else? Because, for instance, direct use of any neural network on a good data set, I can share it with me because it's a subset of this Chameleon. It's always about 90%, whatever you use, whatever kind of a neural network architecture you use, or even classical approach, which is just color co-currents followed by SVM and random forest and such stuff. So please clarify a little bit if possible.
Yeah. We are trying to move from just to classify single patches and then combine the response of single patches to obtain the final decision on the whole slide image to some kind of approach that is able to classify directly the whole image. So there are other methods in the literature, like the one proposed by Tomita and Pellets, but also the performance of those methods are a little bit lower than the one we obtained. The idea was that even if the results are not comparable at the moment with one that is simply worked with single patches, the idea is that to try to reach the same performances by this kind of approach, because we observed that on different data sets, the performance provided by this approach are very far from 97%. We have a project in which we are collecting the images from Pascale, that is a very important hospital in Italy on tumors, and we observed that on the image provided by Pascale, the performance of the methods in the literature are very far from the one that we can find in the paper. And this is the reason because we are trying to overcome this problem by not only considering single patches, but the information coming from the whole image. And by using this protocol, by using this idea, the performance on this specific dataset may be not so high, but it can generalize on different datasets.
Yeah, well, okay. Of course, I do have other questions, like why not to use sliding window technique and doing this patch classification? And,
well, there are no. This is just partitioning. So all patches are disjoint.
Okay, thank you very much. And I put some information in chat so you can see. Do something.
Yeah, but we can also share maybe some discussion information.
Yeah. Our presentation would be on Friday. That's exactly the topic.
Okay.
Okay, thank you very much once more.
Thank you, colleague. So please, if you have other questions, please ask. And of course, do not forget to chat in our Zoom session, so you can exchange your emails and other information. Yeah, we need to be together. Well, as Italians said, chi trova un amico trova un tesoro. Yes. So, okay.
Well, that's for both.
Exactly. So one more question from my colleague, from the guest of our studio now.
Daniel, thank you for interesting reports, because for me, I'm a little confused. You have mixing of different techniques of machine learning. For me, very interesting. You in your convolutional layer, first convolutional layer, input is page like as RGB image, yes?
Yes.
Yes, okay. I can propose you try to another methods because there are the convolution techniques for using gematoxylin coloring and that allow to extract different cell structure. Maybe if you use it before for your first convolutional layer, maybe you take something interesting. By the way, I propose.
Yeah. But yeah, there are some attempts to change, for example, the color space or the original representation of the image, and this is still an interesting topic of research because it is important to know which is the influence of the original representation on the performance, on the final performance of the convolutional neural network.
Okay, that's all. Thank you again, Daniel. So I think we need to proceed with our next presentation, which will be made by one of the co-authors of the paper entitled Chest Pathologies Intellectual Analysis. Please, you have a floor now. Connect your screen, share the screen.
Hello, please let me know when you see my screen.
Yes, it's now connecting. So I think, yes, that's it.
Hi, everybody. The topic of our research is chest pathologies intellectual analysis. My name is Andrew, and I'm going to present you the intermediate results of our research. In the conditions of the pandemic, the primary task of medicine is to detect the disease at an early stage. The solution of this problem is carried out by mass screening of the population. In such conditions, the workload of a qualified radiologist is quite high because they are compelled to handle all patient images. To increase their performance, in this case, a flexible software tool is necessary. It should be as independent as possible from the types of technical devices. That tool is intended for reducing the total number of images to be handled by an expert. The overall process of obtaining and analyzing X-ray images can be represented in the form of the sequence with the following main stages. The first one is collecting data from different radiographic devices. At that stage, it's necessary to support the transfer of data itself and data storing, of course. The second one is image pre-processing. Images from various devices with various setups must be brought to the common view here. Next, we have intellectual data analysis stage, which will be addressed further. At the predictions calibrations, the specifics of medical equipment unit like different voltages, different ampere setups, they all result into the image diversity and also should be taken into account. Finally, there is a stage of actually making a diagnosis. Interpretation and visualization of the results are required here. In addition to that, not only the main pathology, but also the complying diseases should be recognized. We find it necessary to automate that stages as much as possible. Data analysis stage is designed to be performed by a neural network. A well-known architecture called DenseNet was chosen for that purpose. An image with dimensionality 384 times 384 times 3 is fed into the network. And as the result of the transformation performed by the net, the resulting feature description has dimensionality of 12 times 12 times 2084. With the help of linear layers composition, DenseNet feature description is projected into the vector, which with dimensionality matching the total number of lung pathologies under analysis. To interpret the results in the terms of probability as it was required by the process, we consider it's necessary to apply a sigmoid function to that vector component-wise. There is a assumption that is generally not true, but we consider pathologies independent one from each other. One of the possible solutions could be applying so-called label attention mechanism, and this is the scope of our future research. As the result of image analysis, besides pathologist recognition, it's also vital to interpret the outputs of the neural network. So the radiologist should see the result of the classification and why the disease was classified according to the neural network. To interpret the prediction, we use a GradCam algorithm that produces the heat map for the given image, and an example is presented on the slide. Inference, and the inference I mean practical usage of the software package and network, is complicated by voltage and ampere setups that result in image diversity. We try to simulate different setups of medical devices by using extensive data augmentation. The list of transformations applied includes the following: random image sharpness, random contrast, center crops, flips, and different rotations. The first two options mentioned on the slide are suitable to simulate equipment setups, and the final one is intended for network regularization. We have conducted several experiments. The first benchmark data set is RSNA. The approximate size of it is around 30,000 images with classes normal, lung opacity, and non-normal and no opacity. The evaluation results are presented on the slide, and the latter class label is discarded due to its practical irrelevance. The second data set is NIH with total size of around 112,000 images. It consists of 14 pathology labels, including consolidation, fibrosis, effusion, pneumonia, and so on and so forth. The distinctive feature of the data set is that classes are extremely imbalanced. We apply loss weighting technique to combat such kind of problem. The details are presented on the paper. At the slide, you can see the evaluation results for the data set. It's also important to mention that the data set size is quite extensive, so the training set was reduced by us. The idea was to reduce the total number of training samples and preserve image diversity at the same time. All samples were fed through ImageNet pre-trained network of dense net architecture to obtain image vector representations. Then we performed clustering using k-means over that vector representations, and for the new training subset, random samples from the clusters were selected according to the cluster volume. A software package prototype has been developed based on the algorithmic solution of the problem. This prototype automates the process of making a diagnosis, which greatly simplifies the work of the radiologist. The package consists of the following modules. The first one is algorithmic module, which includes calibration mechanism. It is used to tune classification thresholds based on the medical equipment setup. It includes the dense net network, and the pre-processing stage. Then we have a database with verified images and diagnosis to them, split it according to the device they belong. There is also a module for visualization and interpretation of the results, which includes CAM algorithm and operates with the predictions obtained from TensorFlow serving with DenseNet module inside. There is a calibration module and two graphical users interfaces for user and for an expert. As for conclusion, we addressed the problem of chest pathologist intellectual analysis, an approach to solving that problem is proposed, including pre-processing of source images, analysis itself, calibration, and diagnosis making. Experiments have been conducted to confirm the efficiency of this approach using benchmark datasets. Based on the results of theoretical research, a software prototype was developed. As for the future, we plan to include devices setups directly into the training process. As the separate branch of our research, we intend to address that problem as anomaly detection problem by throwing away disease classification and providing an expert just with visualization of anomalous region from the neural network point of view. That's all from my side. If there are any questions, I'll be glad to answer them.
Okay, thank you, Andrei, for your presentation. Again, please ask questions if you have.
Well, maybe if it's allowed, I would like to ask more. Again, this is another direction. There will be, just a little bit later, there will be a plenary presentation. I will have some words and I will tell about that. But using this occasion, I just want to express the wishes to join and to make the benchmarking data set large enough. Because we are now on the internet, we put some service. You can upload images which you want and you will get the result on your computer. But we want to make a sort of competition by ourselves, or challenge by ourselves, and do something better than we achieved each one separately. So that's it. Thank you.
Thank you. Actually, the data set size was reduced due to some technological problems because we do not have enough GPUs to train the network, and we are aware to use Kaggle platform where the time for training is limited by 9 hours. So that's the main reason for reducing the train size.
Well, it could be overcome anyway, the problem. So anyway, the intelligence of people, of scientists, of researchers is more important than power of computers, I believe. Thank you.
Okay, thank you, Andrei, and thank you, Dr. Vasily Kovalyov. I'm strongly remind and would like to advise you to connect to our plenary session, which will be close to the evening, because we will have plenary talk from USA together with our colleague, Dr. Vasily Kovalyov. So now I would like to give a floor to our virtual floor and virtual man, actually, because he just sent us a video because of some external, let's say, problems. Well, I would like to ask our technicians to start a video now.
Hello everyone, my name is Vitaly and I want to present you our report on AI-based retrospective study for revealing diagnostic errors in chest X-ray screening. So in this study, we try to assess the potential profit of using an AI-based X-ray CAD system in clinical practice during screening. Here, when we say CAD, we mean computer-aided diagnosis system, and specifically here we mean an algorithm, automatic algorithm, which can classify X-ray images into normal or abnormal with some confidence, and also to provide some localization, which denotes where the potentially malignant regions are on the image. So there are at least two different ways of doing such a study. One way is a prospective way. When we start using our CAD in real practice, when we see how it works, count how many cases it was useful in how many cases it was misleading, gather the statistics, and then after some time to assess the usefulness. The other way, which is less expensive and easier to do, is a retrospective way, when we use already acquired database of screening, where we have already some X-ray images and we have already textual reports provided by the radiologists in the past for these images. This way we can use our CAD system for the X-ray data and compare the output of the CAD system with the textual reports provided in the past. In terms of the retrospective study formulated in such a way, we pose two main questions. Is the CAD system able to alarm potential misclassifications of X-ray images? Here we mean those cases when an image was classified as normal in the past, but actually there were some signs, some visual signs of abnormalities in it. And the other question is, can a CAD system be helpful in detection of early signs of lung diseases? In this case, for some patients, we have several X-ray images during the timeline, and we can assess maybe if a CAD system was used in the past, it could reveal some abnormalities earlier than it was done by the radiologists in the practice. So for this study, we use a screening database which contains X-ray images of people and textual reports provided by the radiologists. It's a pretty large database acquired from 2 anti-tuberculosis dispensaries. It has almost 2 million records. It has natively digital X-ray images with different resolution and also some metadata. So the textual reports provided by the radiologist usually store information about lung diseases, about possible mediastinal abnormalities, and probable skeleton abnormalities. However, since the database is a screening database, most of the cases there were classified as normal. According to the very strict match with the key phrases from textual reports, we could we could select at least 500,000 of cases which were definitely marked as healthy. So as the CAD system for this study, we used our domestic CAD system, which was trained on a portion of the data from that database. The system provides you with a general abnormality score about the X-ray images, so classifying X-ray images into normal or abnormal, and also it provides some localization information. Anyone can use this, test this system by just following the link below. It's available online. Here is the slide scope of the data used for training. So we had 50 by 50% normal and abnormal cases for the training of neural networks. And the total number of data used was about 33,000, which is less than 3% of all cases. So we can say that we train on a small portion of the database and then apply this algorithm to the large portion of the database, which I will tell you later. So this is the general scope of how we apply the CAD system to the data. So we take the entire database. From the entire database, we select only those which is marked as normal by the radiologists according to the textual reports, and then apply our AI algorithm to all these cases, and then see the outputs and try to analyze. Most of the cases are classified as normal in this case. However, some portion of cases is classified by algorithm as abnormal, and there could be two different reasons for that. There could be just false positive or false alarm for multiple reasons, and there could be some misclassification which tells that actually it was classified as normal by mistake for some reason. And these misclassifications are specifically the cases which we are looking for in this study. So here we see the statistics of the general abnormality score provided by automatic CAD system for these 500,000 of conditionally normal X-ray images. We see that according to the expectation, the majority of cases was classified as normal with abnormality score less than 0.5. However, not significant number of cases was classified as abnormal, and specifically more than 10,000 of cases had score more than 0.9. So to visually, since the task of visual analysis of such cases is still time cost and requires good trained radiologists. We do not analyze all 10,000, for example, or larger amount. In this case, we selected only the top 500 cases with the highest abnormality score and try to find misclassification among these top 500 only. Also, visual analysis of these potentially misclassified cases was performed in 2 stages. On the first stage, these 500 cases were filtered by a non-radiologist to exclude obvious cases of false positive or false alarms. This includes wrong image orientation, reaction of the algorithm to nipple shadows, to some artifacts, bad image quality. There are different reasons. So at this stage, 124 cases were selected for further analysis by the trained radiologist. And the trained radiologist used the images with the original full intensity range. He had access to all the images of the same patient in the database, so he had more information. And his task was to figure out whether each X-ray image is misclassification or not. So after the analysis, visual analysis by the radiologist, 54 cases were labeled by him as the images which had some discrepancy between their X-ray image content and the description in the textual report, which means that there was some misclassification in the past. Here are some examples of this. So here we see on the left the original X-ray image, which was classified in the database as normal image without visual signs of abnormalities. However, we see that the AI algorithm processed this image and marked like a big red spot, something abnormal in the right lung in the middle, and this was confirmed by the radiologist through visual analysis. This is the somewhat similar case, but there is some inclusion in the left lung, and here again in the upper right lung. So these cases were verified by the radiologist that actually they are not normal. And this case is even more interesting. So here you can see the image of the patient taken from 2007, and here the report says that chest X-ray didn't reveal any pathological changes. However, automatic algorithm already revealed something in the right lung. And this is the image of the same patient 1 year after. And here already the textual report says that there is a linear shadow in the lower left lung, so in the lower right lung. And also AI algorithm can detect it. And in this particular case, we see that automatic algorithm could reveal some abnormality before radiologists actually did that in the past. So we had 5 cases confirmed by our radiologist in our study, and they clearly demonstrates that types of mistakes that can be omitted when using a CAD system. So in general, here we trying to say that using a CAD system in clinical practice can increase diagnostic sensitivity and in some cases detect diseases earlier than like without the CAD system. That's all from me. Thank you for your attention.
Okay, well, let's pass our warm hi and warm thanks to Vitaly, virtual hi. And if you still have questions about this presentation, so please type in the chat, because as far as I know, one of his colleagues, I mean Dr. Vasily Kovalov, he is presenting here. If he will tell us some words, or probably it will be later on during the plenary session, well, type questions or whatever. So ask questions just orally now.
Yes, I can answer. There will be questions because I'm also co-author of this presentation. Thank you.
Yep, no questions. I see none. So the next presentation will be given by my colleague in the studio, by Dr. Alexander Nesbis, and now we will try to share the screen. So today I've just asked you to share on the screen, and now I need to do it by myself. So during I will do this. So my colleague will start the presentation, introducing his speech. Okay.
Hello everyone. I'm very glad to see you in this conference, because it's very famous conference, and now I'd like to introduce you reports about analysis of motion of dynamic scene in microscopic images, formulation, criteria, and results. You can see there are many different authors, but every author had troubles today. As a result, I speaker of this report, and this report about research that produced three team, Belarusian team from Belarusian State University, Federal Research Center from Moscow, and also Chinese team. Motion sorry, any troubles. What I'd like about motion. Of course, motion is very interesting fields for computer vision research, because motion include too many possibilities, too many features. By the way, every people usually understand 3D space, geometrical space, and we usually try to spend research in this space. But if you try to look last article about motion, you can find many methods where investigate two frames, two different frames. And of course, you can say there are tracker, but if you look to tracker algorithm, you can find frame by frame analysis, because every frame's connected together. But now we try to find something new and try to look to motion from another point of view. And as a result, we try to describe motion like as complex, something complex, something connected by traditional algebra. And look in this picture, you can see different example of motion. Every motion it construct from different dynamical object. In this picture you can see crowd, and crowd detection. It is last research when we have very interesting success, when we try to describe not motion every people. We try to describe behavior of motion. It is another example. It is motion of car, and you can see different fields, blue, red, and green. When red correspond to direct motion, blue it is seldom motion, and green it is motion to center of group. As a result, we can extract different type of motion, and we can try to describe motion like as a different pattern. Of course, during our research, we try to describe motion, but different element. It is background motion that characterized, but a few different properties: motion of object and motion of group of object. Also present motion of camera. And for example, there are a few types of motion of camera, and you can see a few patterns of this motion. And of course, it is usually simple motion, but if you try to describe it by separate part of motion, we can construct different pattern. Such pattern we can define like as a dynamical object and try investigate it separately. As a result, we can construct a description of scene that include different pattern. We take hierarchy. Hierarchy consists of different part of motion, and step by step we can construct very complex type of motion, not only for separate object but for group, and try to describe different motion effects and behavior of object. Now you can see a scheme for dynamical for monitoring of dynamical object. The scheme consists of 5 stages. On every stage extracted separate features that allow to us construct such hierarchy that I discussed above. And using COFI, we try to make formalization of our motion operation by algebraic elements, and we try spend any formalization of such concepts. You can see in this slide description of construction common motion model from different pattern of motion. As a result, we can reconstruct description for any types of motion. And of course, we can construct algebraic model for dynamical object and try to describe it by connection predicates. Of course, in the basic pattern of motion, it is different features when we contain like as optical flow, flow of vectors inside object, outside object, and outside group and inside groups. Combination of such patterns allow to us describe different element like as aggregation of group, distortion of group, and maybe rotation, maybe something like that. And you real life, like as pattern of object, we can construct separate motion map. In using such motion map, we can try to describe motion in common, not for every object, but it in common for all dynamic scene. You can see this, on this picture, it is a simple example with a simple test when for different dynamics object we reconstruct special map that allow to us describe common behavior. It can used for different type of video. It is not only motion of people and motion of car. It can be histological motion, and also it can be many different tasks. And as a result, we can transform it to special graph of motion and use specific algorithm of clusterization by graph for extract any new features of motion. And what I can say? I can say, in my opinion, it is new point of view to motion. It allows to us construct motion model for description of dynamical scene in common, and it have interesting possibilities because it allows to us maybe optimize our resources for algorithm for calculation of properties and monitoring. Thank you for your attention. Maybe question.
So thank you, dear Alexander, for this exciting movie presentation. Please, colleagues, you may ask now questions. So I see none. Well, actually, Alexander, you see that you're quite at the step to the quite universal algorithm, to universal dream when image processing solve task in any field, well, to analyze motion in cells, motion of cars, motion of people. Is it quite universal? It was a dream in, let's say, a couple of years ago, well, let's say 1 decade, yes? So now you're doing with all of these tasks and to provide algorithms, the same algorithm to solve this task, yeah? Different tasks.
Yes, of course, because I think that I try to find new projection of two motion. I try to look to motion not like as geometrical features. I try to look to motion like from point of time. And I try to take any projection, any pattern that include time axis, and using of it, I try to classify motion but different dynamical elements. Using these elements, we try to create specific algebra for motion and use it for our research, for our investigation.
Thank you. So, colleagues, shall we proceed with the last presentation, I think? Yes, we shall. So the last presentation will be well, let's say B1.6, neural network approach for estimating the level and volume of liquid in transparent containers. And it will, yes, I see that our colleague already opened the screen. Now you have a floor, please.
Hello. As you can see me.
Yes, we can see you. Just make it wider on the full screen and it will be okay.
Okay. The main purpose of our approach is investigating neural network approach for determining the volume of the container and the volume of the opaque liquid in a transparent bounded container. To achieve the purpose, we applied two models of neural network, namely AlexNet and XNet. And we prepared and create a training and test data set for this model. There are four top problems in a similar task when we work with liquid level or volume level in any water or any жидкости, короче. Calculation of the total volume of the container, it's the first problem. When it is necessary to calculate the volume of a certain bounded container, for example, fifths, 200, 1000, and etc. Percentage-based estimation of the fullness of the container, it is consists in getting information about how full the container is. It can be empty, 10%, 50%, and etc. For example, for 100% too. Comparatively estimation of the volume, it is necessary to answer the question of whether it is possible to power of contents of the container into another one. The plain answer option are yes, no, or I can say because there are opaque container in the dataset there. Estimation based on the placement of the container, it is consists in determining the amount of liquid after changing the placement of the container. For example, if it is tiled. The proposed approach processing 5 main stages processing the input image. We send the original image into our detector. We using RetinaNet ResNet 50 from PyTorch TorchVision models pre-training on 91 classes. And we receive the bound capacity, which we send next to bottle volume classification and liquid level classification too. Bottle volume and liquid level classification, it's received by processing one model, AlexNet or XNet. And the final result is a combination of this result and we receive liquid volume and level as you can see. Our data sets. We have two main data sets for our work. The first is the container volume data set, and the second is liquid volume and level data set. We used three main type of bounded container. Transparent plastic bottles with volumes 500, 1000, and 1100. The first dataset contains of transparent plastic bottle without liquid and is only needed for the problem of determining the volume of the containers itself. As you can see, container volume dataset consists of RGB images. All these images we received by using a professional camera, Canon PowerShot S5 AC, and we get 900 images of all datasets, some parts for training and for testing too. And the next dataset consists of transparent plastic bottles with liquids and necessary for the problem of determining the volume of liquid in a container, as well as the problem of determining the level of this liquid. And the same camera and RGB images, but there are some less images for training and testing, but you can see the result is not so bad. Examples of container volume data sets is here. We're using images with different brightness, bottle color, perspective, and any another condition. All of conditions we almost about 10 different conditions that we can 10 conditions. And examples of liquid volume and level data set here. There's always similar condition, and we used not transparent liquid. We used black liquid for good people seeing. Our data preprocessing consists of 6 main steps. First step is randomly change the brightness, hue of images, and contrast. Second is resize the image input size. For XNet model is 48. For AlexNet is 224, and rotate the images to an angle, crop the given images anywhere, horizontal flip the given images randomly with given probabilities, and perform a random perspective transformation of the given image with the given probability. Our deep neural network models. Before I say some words about classification models, I can see that I want to see that we used RetinaNet, ResNet 50 models for detection. After that, we used this classification model. Because classification is this task is more reliable task. We almost don't see anything about detection, because detection it's real easy task. Classification by model AlexNet is the aspects you can see. It's well-known architectures, easy way to find pre-trained models anyway, but they have not a good performance because it have 16 billion terms. Our next model is XNet model. There are more or less params, only 2.5 billion params, input size more or less. That model have a good performance and look like simplified inception models by Google Inceptions. Our test precision of container data set is, you can see 3 parts of approach. On the last approach 100, and accuracy, the most good accuracy received by XNet model is almost 95%. I think it's good accuracy, good precision. AlexNet really good accuracy, but XNet model that we used don't pre-trained. AlexNet model is pre-trained model. And test precision of liquid volume in container dataset similar, but you can see the result is more less. XNet received 86% precision, and there we using pre-trained AlexNet and no pre-trained XNet model too. And we want to say some words about comparison with our concurrents in America. They used context container ResNet model that received accuracy by 52 because they're using not only bottle but any another container types as glass, transparent container, and etc. But we receive more good precision, and it's nice. And some examples results of our works you can see on the screen. Thanks for your attention.
So thank you. Thank you very much. Yeah, please mute your microphone. Now I would like to ask our colleagues to present the questions, to ask questions.
Yegor, thank you for your interesting report, but when I listen you, I see that you talked about different type of liquids, but every time liquids have color, different color, black, yellow, and something like that. But what about transparent liquid? For example, water on vodka and something like this.
We use only plastic bottle transparent, and they have some color green, orange, but all of this color must be some transparent because we can't see any liquid level in bad transparent bottle or any another type of container. If I understand you rightly.
Thank you.
Yeah, it's clear. Any other questions? Okay. Well, if none, I would like to say that now we have a break. You can brief twice or 3 times because it will be just only, let's say, 12 minutes. And in 4:15 p.m., we will come back to have a final session, a plenary session, and I'm sure we will enjoy with this. So please come back in 4:15 p.m.
Please.
So now, colleagues, I'd like to open the final session. So this is a plenary session, and the chairman of our plenary session, Professor Alexander Tuzikov. So I give you a floor, if you do not mind.
Okay, thank you very much. I would like to announce our plenary session and presentation towards artificial intelligence-based diagnosis of lung tuberculosis, TB portal, where traditional medicine joins forces with artificial intelligence, 3D visualization, genomics, and data mining. This presentation will be jointly done by Andrei Gabrilian and Dr. Vasily Kovalyov. I would like to shortly introduce our key speakers for this session. Andrei Gabrilian is working in the National Institute of Allergy and Infectious Diseases of the National Institute of Health in United States of America. He is a bioinformatics specialist with more than 30 years experience, studied and worked in Europe and United States, and he participated in many pioneering projects, including well-known sequencing and annotation of the first human genome project. Now Andrei is responsible for TB portal program in the National Institute of Allergy and Infectious Diseases, and he will tell about main activities done in framework of this project. Dr. Vasily Kovalyov is working in the United Institute of Informatics Problems of the National Academy of Sciences of Belarus. Vasily has more than 30 years experience in the field of imaging, image processing, pattern recognition, and now he is head of laboratory of biomedical imaging in our institute, and he had a great experience working abroad in Germany, Korea, and United Kingdom, but came back and now is actively working in various projects, teaching at the Belarusian State University and doing many interesting projects with the students and master students of Belarusian State University. So I would like to give the floor now to Andrei Gabrilian. Please, Andrei.
Well, Andrei, we agreed that I'm doing kind of introduction and then you're going specifically for TB portals. Is this correct?
Yes, I wouldn't call it introduction. You will be talking about real science. And then okay. I will just talk about the framework. Yes.
Okay.
Please go ahead.
Thank you, Andrei.
Please.
So that's part number one. And the title you see, it's already voiced the title. So let's go ahead. Let me start with a very brief introduction of our department, which is biomedical image analysis. And you see different kind of images we're dealing with, etc. And also, for the beginning, I will just highlight a couple of just two different research directions which we consider to be interesting, and we are doing something on that. So the first is using generative adversarial networks, so-called GANs, for generating of artificial medical images. Why should we do this? This is because the medical image, some kind of data which is very much restricted and prohibited by law to use in different scenarios, etc., etc. So the dream is just to learn how to generate artificial images to replace the real ones where it is possible. So that's on the left. It's shown, for instance, generating of artificial X-ray images of chest. and to understand why we need so many of them, why we need so huge database. That's very simple example. People are, patient could be male and female and somebody else, I don't know, but at least you need at least two, this case you need two different GANs to generate separately male and female. But also there are methods when you just supplying the image as such and saying the kind of a switch, which saying gender of this person, and then you train in one GAN, but in limit, in our case, we also examine different ages people for 1 year of life from 20 to 30. That means we've trained 50 GANs, what is difficult. And so we tried different approaches which already exist. The first, and I would say classical, but classic is just few years for this classic. It's so-called deep convolutional GANs, and we produce images like that, which are not bad. And then we also tried so-called progressive GANs, pro-GANs. So they start, in this case, the image starts from just 4 by 4 pixels, and then they are subdividing and getting more fine and more refined, and then finally the process stops. And we found that this still works better in this particular case. So we put all these services, and not only this one, but other also in our website, which is called image.org.by. And I invite you to visit that functionalities, try, criticize, etc., because not everything is working perfectly here. It's just, artificial histological images looking nicely, but that image is, we are trying to do post-processing, not just generate from random vectors. And another problem which we are researching in is are adversarial attacks to deep convolutional neural networks. So deep means sounds like it's good, they are deep, but it's create more and more chances for adversarial attack. The attack is done by modifying our original image, modifying in the way to make it, to force the neural network to make a wrong decision. Like a healthy person will be diagnosed as a pathology and CT and X-ray and some other, like this one, histology. So on the left, original, on the right, it's modified. It's unlikely you will find the difference, but the cancer, that's the clearly cancer, and then it's diagnosed like norm, and vice versa. So that's a very important problem, and we examined both scenarios like black box and white box attacks. Second case, we know the architecture of the network which we're going to attack. So that's original images again on the left. On the right, it's attacking image. And we examine different kind of architectures on different kind of images, not only this one. Don't think this way. It's more than 1 million images in total involved in this experimentation. So that's the quickly what we are researching on. Now let me start the main part of my part, which is lung disease diagnosis, and specifically tuberculosis. By the way, we need to understand that there is not just something specific tuberculosis, and that's in lung. There are different kinds of abnormalities in lung, which may and may not be associated with tuberculosis. So we may not be so narrow. We need to be broad to cover the problem of diagnosis of lung tuberculosis. And this is naturally subdivided for screening, like screening in most of the countries where it is, it's done by X-ray, except United States, where it's done by CT. And treatment, where normally doctors using, radiologists using computer tomography. So we will be talking about both of them separately right now. So in our country, for instance, it's already mentioned somehow that we have a massive screening, which is lasted more than 10 years, and it's computerized. That's naturally, natively digital images. They come in by network to certain medical hospital, and then the results going back. And first, to start with the land diagnosis, we need to extract land first. So that's commonly known problem of segmentation. We are working many years already on the problem. We start with the classical approaches, and then with this non-linear image registration segmentation based, on which the segmentation is based. And then last years, we are more and more on the using the convolutional neural net architectures of different sort, and of course combining all the advantages where it's possible of another approaches. That's a figure which just illustrate, you will immediately recognize this is something like UNet. So UNet is now much wider. People who doing that, they develop it further, but nevertheless. So that's example of land segmentation, which just first step to do something with land. We need to extract it first. Then that's very briefly about our solution. So the solution is not just first, not the second. There are several solutions, and we gradually improve our quality of diagnosis using different kind of architectures, different kind of network and combinations of them, and so on and so forth. As already Vitaly in previous talk, the member of my group, former, we, doctor and everyone actually not need just only probability or abnormalities or lesion in the lung. The person need also to point out where it is. So we producing, along with that probabilities, we also producing heat map to point out the attention where the decision comes from. You see, one is totally good, another one is so bad, I mean lung. So that's examples of heat map. They're very first, but I like them how they appear. The heat map is not cut just to remove everything except lung, but still it looks nicely in my view. And this, this solution is now available for free on our website, so you can upload your own image and get the result. And already there are 2 countries, except Belarus, 2 abroad countries who doing that and testing their own images. And that's, of course, technical problem, because for different format, different traditions to store the images, all that kind of things. So the second portion, second work, that's CT, computer tomography. And we detecting, we need to automatically detect lung abnormalities. They call lesion in English. And I will first tell you about data preparation. So it's roughly 3 stages. First stage is just identification of cases which are of interest. This is naturally different kind of abnormalities coming with very different frequencies in hospital. So to have a balanced data set, a good quality data set, we need to identify which patient is interesting, which is not interesting, just to get the result. And then second stage, which is done by high quality radiologist who is working with us and Andrei and with all our project. And he pointed out different kind of lesions, and then trained non-radiologists, they doing final wording, because we need in many occasions. And this is the kind of lesions which we are dealing with. And at the very last time, we also include COVID-19, which is a general disaster nowadays. So, and as usual, the segmentation, the analysis starts from segmentation of lung. Some people doing segmentation of lung a couple of times on healthy subjects. That's going pretty straightforward, pretty well. Believe me, in norm, everything is going much more easy. But in case of pathology, then the problem really starts. It's really difficult to accurately segment the lung itself. And then we need to go inside the lung and to find out lesions, abnormalities. And that's it's also done with the neural network. It's also available now, you see, it's also available now from our website. Of course, CT is heavy image, and there are some limitations. You need to good internet to upload. You need to permission for dealing with this patient to put it somewhere outside of your office, etc., etc., etc. But it's not our end. We need to just deal with them. And of course, you on website, you would be able to review somehow the segmentation results. So there is a kind of viewer, which is also web-based viewer. You can do it just from your computer without installing any software. Once we got this kind of extraction of and estimation, the quantities of lesions, of abnormalities in lung, then we can do also content-based image retrieval. But this is retrieval, not just similarity retrieval by visual appearance. It's medically meaningful searching, which is capitalized on the information on how many lesions, where they are, how big they are, etc., etc. Then the similarity it's treated also would be supported by doctor. Otherwise, its visual similarity may help, but may not. Last times we also looking at lesion segmentation with lesions which are associated with COVID infections. So that's on the left. You see, recently we take part in a large international competition, and we got in top 10 with the position number 6. So on the left, you see the lesion which is segmented by doctor. On the right, you see lesion which is segmented by software, and that's the approved. That's some certificate which says that this particular member of group was leading that submission, that development. Actually, we submit 3 different solutions. So that one was the best. And I think all top 10 now using UNET, and then clever guys from Heidelberg, from German Cancer Research Center, the KFC, they introduced new versions, and UNET, it's a version of UNET, which is optimizing parameters by itself. So you know that problem. It's also somehow included in the last version. And finally, I came to the point when I will give the floor to Andrei, but before that, I will just in 1 minute, I will click on our website. So that's image.org.by, that's the team, and that's different kind of things we have put there, like this CT diagnosis online. You see the result, then you can register and see in more details. And also Andrei will add what is possible to do in portals, because they are large nowadays. And that's okay. Daniel, you was interested about histology, so that's in spare time. I can show you how does it works. It's also available from web, so you can that blood. That's the blood clearly, etc. And then you can do something like a classification, etc. Right here. And also, you can upload your own. I will not do this. I will just do that. Yeah, it's clear. It's good. So that's it, Andrei. Now it's your turn. I will stop sharing my screen.
Thank you very much.
You're welcome.
Now let me see. Here.
by the way, within my 15 minutes.
Okay.
Yes, now we
so
see
I want to switch gears now and tell you about Tuberculosis Portals, our international program and resource that supports research and integration of artificial intelligence predictions among other data types for better understanding and more efficient treatment of tuberculosis. Why we are so interested in tuberculosis? Clearly, from point number 2, we are living in the 21st century, and yet TB manages every year to claim more than 1 million lives. Now, if you extrapolate that figure to human history, you will see how terrible and damaging the disease was for the humankind. The World Health Organization launched its End TB strategy in 2014 with the aim to cut TB incidence by 90% by 2035.
Excuse me,
Brilliant. Let me switch to the slideshow.
Yes, exactly. It's better to switch to right screen.
I'm sorry.
That's okay.
Let me see now. Can you see my screen?
Yes.
Perfect. Yes. Now, WHO reminded us, in the words of Dr. Teresa Kasaeva, Director of Global TB Program, that enhancing and optimizing global data sharing efforts is critical to make the most of the existing evidence. We cannot beat tuberculosis alone. No country can do that. So only the joint efforts can do that. And this is why TB Portal program was born, was spearheaded by National Institute of Allergy and Infectious Diseases. Our mission was to create a network of global shared informatic resources to advance the understanding of tuberculosis as a disease and to contribute to development of new and efficient early diagnosis and improved treatment with an emphasis on multi-drug resistant tuberculosis, the worst kind of tuberculosis that does not answer well to most efficient drugs that we have right now. We started years ago, and I'm glad to tell that the first hospital and the first institute that joined the TB Portals program were from Minsk, from Belarus. Currently, we collaborate with doctors and researchers in 15 countries, and we have also discussions with 3 additional countries. Here is the map that gives you the outlook on our sites worldwide. Next slide gives you some view on how many cases we have now. We are closing on 10,000 cases, 10,000 records that are pretty complete. They're patient-centric data, meaning that we know everything about the patient. We know the microbiology. We know the clinical data. On the right side, we can see that we also collect genomic data about the pathogen. We have imaging. And what is important and what is unique for our database, that we also store and present the artificial intelligence-based annotations of these images. We collect biochemistry data, and we also venture into new domains, including transcriptomics and microbiome data. Here, on the next slide, we see the schematic view of how the program works. It all starts with the data collection that is on top. People send us the data. The centers send us the annotated data. Then we and other researchers analyze the data. So essentially, we're doing the extracting knowledge from the data. And with this knowledge, after the analytics part, we are trying to answer important questions that doctors working with tuberculosis might have about the diagnosis, about genomic evolution of pathogen, about the factors that are associated with successful or unsuccessful treatment, etc. Importantly, TB Portals program makes all data that we collect together with computed data and predictions, which is our added value, openly available for research purposes. Of course, we do not collect personal data or share them, and we closely monitor the anonymity of all tuberculosis patients that we have in the database. We provide downloads of entire database or its parts via Aspera or APIs. We develop our own open access tools and resources where people can analyze TB Portals data and their own data. So here is one of our resources. It's our cornerstone. It's a case browser, which works pretty much like the collection of records of data from tuberculosis patients. And it also includes the annotations that were done by the algorithms that were described by Dr. Kovalov. Here is probably you cannot see because it's kind of a low resolution and too much information on one page, but every page, every record has the data for individual patient that consists of socioeconomic data, drug susceptibility testing, treatment history, outcome, comorbidities. Very important on the left side, you can see the time line of the treatment and tests and radiological investigations that were done during this course. Now, coming closer to the images that we're talking about, we have several kinds of annotations. We have annotations provided by radiologists, and we have now the artificial intelligence labeled lesions annotations. So some might ask, why are we so interested in artificial intelligence and these algorithms? The truth of the matter is that annotations by radiologists are very diverse, and there is no good consensus. This is not my opinion. This is known historic fact. So clearly, in tuberculosis and in other diseases, there is a need for the precise, general, and very stable artificial intelligence supported predictions of various features associated with the diseases. Here you can see an example of the record that has been annotated by artificial intelligence. You remember this from previous presentation, how it was done. For tuberculosis cases, we have predictions of various features associated with tuberculosis, such as foci, caverns, fibrosis, pleuritis, atelectasis, and pneumothorax. They are color-coded and overlaid on top of existing slices of CT images. And also we have the similar images for each of the annotated images, again, as presented by Dr. Kovalov. Now, we, of course, were testing the predicted and manual annotations with the ultimate goal, ultimate goal of our database and our research project, namely how all this correlates with the treatment outcome. Because if we can compute features that are highly correlated with the outcome, then we can flag soon enough the problematic cases and help doctors to identify necessary changes in treatment and so on and so forth. So we published some papers. This is one of the recent ones where we analyzed how the treatment outcome correlates with the computed tomography observations provided by radiologists, and we found pretty good correlations. So it was very good results. And this is why we enthusiastically support further integration of both radiologist and artificial intelligence annotation into the TB Portals program. Once again, this is what makes our TB Portal database unique. Now, in many countries, CT is still too expensive for mass screening, but fortunately, X-ray investigations are cheap enough and plenty informative. TB Portals also collects X-rays together with CTs for histories of disease. And years ago, we joined forces with a company from India called CURE.ai that developed AI-based X-ray analysis system for TB diagnosis and predictions of TB-related features. So their database was very extensive, hundreds of thousands of X-ray images, but India had mostly drug-sensitive tuberculosis. So we're not sure how it would perform on our database, which is rich in drug-resistant cases of tuberculosis. First thing that we did, we checked their predictions on our database, and results were pretty good. Turned out to be very promising. Here is the publication that pretty recently supported the integration of CURE.ai annotations into TB Portal's database. And very fresh news. So this is a September publication of this year, where CURE.ai together with other 4 prediction systems were tested on pretty large data set. So it was 23, well, almost 24,000 individuals that were included in the analysis for prediction of tuberculosis. And what is interesting, that is all 5 artificial intelligence algorithms significantly outperformed the radiologists, but only the algorithm that is that was done by CURE.ai and another algorithm that was provided by CAD-TB, CAD4TB, were able to meet the WHO's recommended target product profile of triage tests, which is more than 90% sensitivity and more than 70% specificity. So we are looking forward to continue this collaboration as well. Now, diagnosis of tuberculosis is not the end game, because even when diagnosis is right, the treatment can be problematic, and the cure rate can be, especially in cases of multiple drug-resistant tuberculosis and extensively drug-resistant tuberculosis, is about 50% and could be as low as 30%. So it's very important to analyze continuously what is going on with the lungs, and this is where we are moving with our collection of the data, trying to build models that would tell us and doctors in advance if something is going wrong. Also, even when the person is seemingly healthy and released from the hospital, there are some chances, and depending on the country and TB burden in it, from 5 to 30% chances that TB may relapse. So again, we will be looking at CTs and X-rays for additional information about whether the patient might still have something in the lungs that would be evidence of tuberculosis not being completely cured. So these are our directions for the future. So this is why we are increasingly getting into the investigation of disease dynamics. So we are toward the analogy where moving from photos and snapshots to movies. And here is an example of morphing of several consecutive X-rays from the same patient. So on the right side, which is the left lung, you can see on the top that the cavity, which was pretty prominent in the beginning of treatment, shrinks towards the end of the treatment. So, and this is great, this is good. We know that the treatment works and the patient has been successfully cured, but it's not always the case. So making these movies, videos, and presenting them to doctors and students is very important and informative. Lately, we were going even further with 3-dimensional images. So from CTs, we begin to develop three-dimensional models of lungs from TB Portal's collection. And of course, we attach the information about treatment, timeline, clinical findings, so it all is integrated together. This is a snapshot of a three-dimensional model that we have. So this is 45-year-old male smoker, initially diagnosed with tuberculosis, empirically treated for drug-sensitive tuberculosis. And you can see that in the lungs, this is the radiologist-provided annotations, there was a fair amount of infiltrate and the foci that were in the right lung here. However, after the treatment, 1 month into treatment, we can see that the bad area shrinks significantly. And we know that over the course of 2-year therapy, this patient was successfully cured. Now, that was manual annotation. And we were, of course, interested how the artificial intelligence annotations provided by Dr. Kovalov's group will work in this case. And they worked pretty well. So they identified very nicely the area where the infiltrate and fibrosis was located, and also correctly identified the shrinking of the bad area into treatment. So clearly, artificial intelligence predictions, as we saw from X-ray example and CTs, have good future and very promising future, and we will continue to integrate this information into our resource. This model and other models are already available for everyone on our TB portal. We're working on 10 additional models that will highlight various forms of tuberculosis and types of treatment. You can come and see for yourselves. We'll be glad to hear from you and answer your questions. With this, I want to thank you for your attention, and also thank my colleagues and friends, the great TB Portals team that continues to work on growing, improving, and expanding our data and our resources. Everything that I presented today is, of course, teamwork. All the best. Stay safe, and hope that next year we'll all be able to meet in person in beautiful Minsk. Goodbye.
Thank you very much, Andrei, for your very interesting presentation. We would like to ask participants of our conference to ask some questions to you. Okay, please, colleagues.
I see none.
No.
Yeah.
Maybe I can ask one question. Could you say, Andrei, as it follows from your presentation, so it's possible with high probability diagnosis tuberculosis by X-ray images, or it isn't? I mean that
it's possible
to say from X-ray images whether it's tuberculosis or pneumonia or maybe other lung diseases. So it's possible or not? I haven't understood now.
Okay, my question. No, I cannot answer question with questions. So I will tell you, it depends. It depends on how long the disease was taking the course. If the person was just infected with tuberculosis mycobacteria, then the damage for the lungs is not done. The pathogen is already in the system. Your immune system already responding to it. You can find the pathogen in the sputum, but the lungs might be still not damaged. In this phase of the disease, it's difficult to diagnose anything. However, as the disease takes its course, the small nodules and then further the larger cavities might appear in the lungs depending on the host. And then it's easier and easier and easier to see that, yes, indeed, this is tuberculosis. So depending on how bad is the situation, it's either very difficult or very easy to diagnose tuberculosis. So one test, X-ray or CT, is not enough. It always probably will be a combination of microbiological methods, blood tests, and radiological information. Sorry for the long answer.
Okay, thank you very much. And another question is concerning TB portal. So this portal contains various information, clinical data, images, genomic data. And do you know whether for other diseases similar portals are available in the internet, or it is a unique portal for TB?
I'm happy to say that it is a unique resource. And as I said, it is patient-centric. So if the patient is in TB portal, we know everything about this patient. And it means that we know, for example, images, and we know the genomic content, the genomic outlook of the pathogen that invaded this person. We also know the lab tests and so on and so forth. We do not artificially grow our database. We do not download, for example, additional genomes from GenBank because we don't know anything about the patients from which these pathogens have been sequenced. And therefore, we cannot make any inferences, like, did this patient died? What kind of drugs he was treated with? How long into the treatment this pathogen has been isolated and sequenced? So we are trying to create the unique database, which is the most complete and productive database for research. And as I said, I would like to express my admiration for the support that we're getting from our researchers worldwide. And the collaboration with Belarusian team has been extremely, extremely productive and fruitful. Thank you very much for your support.
Okay, thank you very much once more for your presentation. We will see whether there are any other questions or no.
No, we have none. Yeah, we have none also in chat.
So we can finish our plenary session. I would like once more to thank very much our distinguished speakers and for this excellent presentation and this excellent job. Thank you very much.
Thank you. So in my turn, I would like also to thank you, dear Andrei, that you was able to be here in afternoon session. So now, according to the lack with the USA, so you have completely different time, but still. So yeah, now we see your face. Okay, that's good. Finally. Well, on this note, quite nice high notes. I'd like to say thank to all of you. So we have very productive session. And now we can finish this day. And say to each other goodbye and see you tomorrow. But before you will disconnect, I would like to say that in 1 hour we will start our informal meeting, let's say virtual cafe. The link is in your emails, or as for audience, YouTube audience, you can just chat. You can drop a message to the Telegram chat, or here in YouTube chat on Zoom at the moment. So I will send an ID. You can join us to spend some informal time on the internet cafe, which is provided by Bosnet and Jan servers Edumit. So now I'm only one who's between you and evening. So goodbye. Thank you. See you tomorrow.